In the history of physics, few discoveries have had as profound an impact as Isaac Newton's formulation of the laws of motion and the law of universal gravitation. These groundbreaking insights not only revolutionized our understanding of the physical world, but also laid the foundation for classical mechanics, a framework that would dominate science for over 300 years. Newton's ideas continue to be fundamental to our understanding of everything, from the movement of planets to the launch of rockets. The story of Newton's discoveries is often told with the iconic image of him sitting under an apple tree, watching an apple fall to the ground. While the tale may have been simplified over time, it encapsulates the essence of Newton's curiosity. Born in 1642, Isaac Newton was a mathematician, astronomer, and physicist who sought to answer the most fundamental questions about how objects moved and interacted in the universe. At the time, no one had a clear understanding of the forces that governed the motion of objects, either on Earth or in the heavens. As the story goes, one day, Newton observed an apple fall straight to the ground, which led him to ponder why the apple fell downwards rather than sideways or in some other direction. This seemingly simple observation sparked a chain of thoughts that would lead to one of the most important breakthroughs in the history of science. Newton realized that the force that caused the apple to fall to the ground must also be the same force that governed the motion of the moon in its orbit around the Earth. This insight would form the basis for his theory of gravity. Before Newton, philosophers and scientists had proposed various theories about motion, but they lacked a unified mathematical explanation. Newton's laws of motion, introduced in his seminal work Philosophiae Naturalis Principia Mathematica in 1687, created a comprehensive framework that described how objects move and interact under the influence of forces. These laws still serve as the foundation for much of classical mechanics. Newton's first law states that an object at rest will remain at rest, and an object in motion will continue moving with the same speed and in the same direction unless acted upon by an unbalanced force. This principle of inertia was a revolutionary idea, as it challenged the previous Aristotelian notion that objects in motion naturally come to rest unless continuously pushed. Newton's insight revealed that objects would keep moving indefinitely in a straight line unless something, such as friction or gravity, stopped them. Imagine you're sliding a hockey puck on ice. In a frictionless environment, the puck would continue sliding forever in a straight line unless you hit it with a stick or some other object intervenes. Newton's second law describes how the velocity of an object changes when it is acted upon by a force. It states that the force exerted on an object is equal to its mass times its acceleration. This equation gives a quantitative relationship between force, mass, and acceleration, providing the foundation for how we understand how forces influence motion. If you try to push a shopping cart and a car with the same amount of force, the cart will accelerate much faster because it has much less mass. Newton's second law explains why this happens. Newton's third law asserts that for every action, there is an equal and opposite reaction. This law applies to all interactions between objects, whether they're in contact with each other or acting at a distance. When you push on a wall, the wall pushes back with an equal and opposite force. You might not move the wall, but the force is still there, and it's pushing back with the same strength. These three laws formed the backbone of Newtonian physics, providing a way to predict how objects would move and interact under various conditions. Whether it was the motion of a car or the trajectory of a planet, Newton's laws allowed for precise calculations of forces and movements. While Newton's laws of motion provided a framework for understanding the motion of objects, it was his discovery of gravity that truly changed our view of the universe. Newton proposed that every object in the universe exerts an attractive force on every other object. This force, called gravity, decreases with the square of the distance between two objects. What made Newton's law so revolutionary was that it applied not just to objects on Earth, but to all objects in the universe, including planets, moons, and stars. Newton had bridged the gap between terrestrial mechanics and celestial mechanics. He showed that the same force that causes an apple to fall to the ground also governs the orbits of planets and the motions of moons. This was a bold and far-reaching insight that unified the heavens and the earth under one universal principle. Newton's laws transformed the way we understood the universe. His work provided precise explanations for the orbits of planets, the behavior of projectiles, the motions of tides, and much more. It laid the foundation for later discoveries in physics, from the work of Albert Einstein on relativity to the discovery of quantum mechanics. Newton's laws also had practical implications. For example, understanding motion and gravity enabled the development of technologies like space travel and satellite communications. When humans first set foot on the moon in 1969, it was Newton's laws that made that possible. Modern rockets and spacecraft are designed based on these very principles. Despite the overwhelming success of Newton's laws, they weren't the final word in our understanding of the universe. In the 20th century, Albert Einstein's theory of relativity provided a more comprehensive explanation of gravity, particularly in extreme conditions such as near black holes, or at speeds approaching the speed of light. However, even in the face of these advancements, Newton's laws remain remarkably accurate in many practical situations and continue to be essential in fields like engineering and everyday physics. Isaac Newton's laws of motion and his law of universal gravitation represent one of the greatest intellectual achievements in the history of science. Through his brilliant synthesis of earlier knowledge and original insights, Newton not only explained the workings of the natural world, but also provided a framework that continues to shape our understanding of physics today. From the fall of an apple to the motion of planets, Newton's laws have helped us unlock the mysteries of the universe, and they remain a cornerstone of science, guiding everything from engineering to space exploration. Discovery of thermodynamics and the laws of heat. In the 17th and 18th centuries, as machines began transforming the world, scientists started noticing something fascinating about heat, work, and energy. The Industrial Revolution brought engines that needed fuel and created power, driving ships and factories. Yet, despite all their practical skills in building these machines, engineers and scientists couldn't fully explain why some engines worked better than others. This sparked a revolution in understanding how heat behaves, known as thermodynamics. The story begins in the early 19th century with a French engineer named Sadi Carnot, often regarded as the father of thermodynamics. Carnot wanted to improve steam engines, which were the beating heart of the Industrial Revolution. To him, heat was a mysterious fluid that flowed between objects, carrying energy along with it. In 1824, he wrote a small book where he introduced the concept of the ideal engine cycle, now known as the Carnot cycle. Although Carnot didn't have the complete modern understanding of heat and energy, his work laid the groundwork by posing essential questions. Why can't an engine be 100% efficient? Where does the lost energy go? Carnot's insights inspired others to dig deeper. Soon, scientists like Rudolf Clausius, William Thomson, and James Joule expanded upon his ideas, leading to the formulation of the fundamental laws of thermodynamics. They realized that energy, in all its forms, follows strict rules that govern everything from boiling water to burning stars. The first law of thermodynamics states that energy cannot be created or destroyed, only transformed. This idea, called the conservation of energy, was solidified by James Joule in the 1840s. Joule conducted a simple but brilliant experiment. He attached weights to a paddle wheel submerged in water. As the weights fell, they turned the paddle, stirring the water and causing its temperature to rise. Joule measured the temperature change and concluded that the mechanical energy from the falling weights was transforming into thermal energy in the water. This law marked a huge leap in scientific thought. It meant that energy is like currency. It can be spent, saved, and exchanged, but it never disappears. Whether it's chemical energy and fuel, thermal energy as heat, or kinetic energy as motion, all forms of energy are convertible but conserved. Rudolf Clausius took thermodynamics to the next level with the second law, which states that in any energy transfer or transformation, entropy, or disorder, will always increase in an isolated system. Clausius's work in the 1850s formalized this idea, showing that while energy is conserved, it tends to spread out, moving from concentrated to dispersed states. To make sense of this, imagine an ice cube melting in a warm room. The heat from the air flows into the ice, melting it into water. The second law explains that heat will naturally flow from a warmer area, the room, to a cooler one, the ice, and never in reverse. The disorder increases as the energy spreads out and the ice melts, representing a higher entropy state. This law tells us why time appears to move in one direction, why your coffee cools down, and why a broken egg doesn't put itself back together. Entropy gives us the arrow of time. In the late 19th century, as scientists probed even deeper, they discovered the third law of thermodynamics. This law, proposed by Walter Nernst, states that as the temperature of a system approaches absolute zero, 0 Kelvin, or minus 273.15 degrees Celsius, its entropy approaches a minimum value. At absolute zero, a system would be in a state of perfect order, with no random motion among its particles. While absolute zero is theoretically achievable, in practice, it's impossible to reach. The closer you get, the harder it becomes to remove the remaining energy. This law helped physicists understand the behavior of materials at extremely low temperatures and opened doors for research into superconductors and quantum states of matter. Interestingly, the zeroth law of thermodynamics was formalized last, even though it's foundational. It states that if two systems are each in thermal equilibrium with a third system, they are in thermal equilibrium with each other. This law allows us to define temperature as a measurable, transitive property, making thermometers meaningful tools. Without it, comparing temperatures would be inconsistent and unreliable. These laws aren't just scientific curiosities. They're the backbone of how we understand and harness energy. They explain why engines need fuel and why refrigerators keep food cool. They shape everything from chemical reactions to the life cycles of stars. Without thermodynamics, the engines powering cars, the turbines generating electricity, and even our body's metabolic processes would be incomprehensible. Thermodynamics also gives us a glimpse into the fate of the universe itself. According to the second law, the universe is constantly increasing in entropy. This points toward a future heat death, a state where all energy is evenly distributed, and no work can be done. Stars will burn out, and matter will be scattered thinly across space, leaving a cold, dark cosmos. From its roots in the study of engines to its role in defining our universe's ultimate fate, thermodynamics is a profound framework. It teaches us that while energy remains constant, it naturally spreads out, creating complexity, fueling life, and driving the evolution of the cosmos. Discovery of Electromagnetism. The story of electromagnetism begins in the early 19th century with a simple yet groundbreaking observation. Electricity and magnetism are not separate forces, but deeply interconnected aspects of the same fundamental phenomenon. This idea, which seems straightforward today, was revolutionary for scientists in the early 1800s, and its discovery changed the way we understand forces in the natural world. In 1820, a Danish physicist named Hans Christian Ørsted was teaching a class on electricity when he noticed something unusual. When he brought a compass near a current-carrying wire, the needle moved. This was strange, as compass needles are generally influenced only by magnetic fields. Ørsted's simple experiment revealed something profound. An electric current can create a magnetic field. With this, the field of electromagnetism was born. Before this, electricity and magnetism were seen as completely separate phenomena. Electricity was the flow of charge, seen in batteries and lightning, while magnetism was associated with materials like lodestone and observed mainly in natural magnets. Ørsted's discovery hinted that the two were connected, a spark that led scientists around the world to dig deeper. Michael Faraday, an English scientist, was one of those who pursued Ørsted's discovery. Faraday was fascinated by the interplay between electricity and magnetism, and his experiments took Ørsted's initial finding much further. In 1831, Faraday made a landmark discovery. Moving a magnet near a coil of wire could induce an electric current in the wire. This phenomenon is known as electromagnetic induction. To understand Faraday's work, imagine moving a bar magnet quickly in and out of a loop of wire. As you move the magnet, it disturbs the space around it, creating a changing magnetic field, which in turn creates an electric current in the wire. This was the basis for electromagnetic induction and would become the foundation for all electric generators and transformers. Faraday's insight was transformative. If moving a magnet could produce electricity, it meant that electrical energy could be generated, transmitted, and manipulated in ways previously unimagined. Faraday's work laid the groundwork for the development of electric power, a technological leap that powers cities, homes, and industries to this day. While Faraday made these key discoveries, he didn't fully develop a unified theory of electromagnetism. That achievement would come with James Clerk Maxwell, a Scottish physicist whose work in the mid-19th century brought all these ideas together into a single, elegant framework. In the 1860s, Maxwell synthesized the discoveries of Ørsted, Faraday, and others into a set of 4 mathematical equations, now known as Maxwell's equations. These equations describe how electric and magnetic fields interact and propagate through space. They reveal that changing electric fields can create magnetic fields and vice versa, forming a self-sustaining wave. This is the essence of electromagnetic waves. Maxwell's equations showed that light itself is an electromagnetic wave. This meant that visible light, radio waves, X-rays, and all other forms of electromagnetic radiation were part of the same spectrum. This insight was groundbreaking. It united optics, the study of light, with electricity and magnetism, bridging disciplines and creating a single, coherent framework for understanding the electromagnetic spectrum. The practical implications of electromagnetism are nearly endless. Faraday's discovery of electromagnetic induction led directly to the creation of generators and transformers. By moving a coil of wire in a magnetic field, generators can convert mechanical energy into electrical energy. This principle is the backbone of modern power generation, from coal-fired power plants to wind turbines and hydroelectric dams. Electromagnetism also forms the basis for electric motors, which operate by converting electrical energy back into mechanical energy. Motors use the interaction between current and magnetic fields to create rotation, powering everything from household appliances to industrial machinery. The development of telecommunications was also made possible by understanding electromagnetic waves. In the late 19th century, Heinrich Hertz demonstrated the existence of radio waves, confirming Maxwell's theories. Soon after, inventors like Guglielmo Marconi found ways to harness these waves to send signals wirelessly, leading to the invention of radio. Radio waves, microwaves, and eventually fiber optics would reshape communication, making it possible to send information across vast distances instantaneously. Electromagnetism isn't just useful for human technology. It's a fundamental force that shapes the natural world. From the Earth's magnetic field, which protects us from solar radiation, to the chemical bonds holding atoms together, electromagnetism plays a key role in the structure and behavior of matter. Consider, for example, how electrons orbit the nucleus of an atom. This arrangement is governed by the electromagnetic attraction between negatively charged electrons and positively charged protons. In this way, electromagnetism binds atoms together to form molecules and ultimately the matter we see around us. Without electromagnetism, there would be no structure in the universe as we know it. The auroras, or northern and southern lights, are a stunning example of electromagnetic phenomena. When charged particles from the sun collide with Earth's magnetic field, they spiral around the magnetic lines and collide with molecules in the atmosphere, creating vibrant displays of green, blue, and red light. These phenomena remind us of the invisible, yet powerful forces at play in our universe. Electromagnetism is not just a branch of physics. It is one of the pillars of modern science and technology. From its discovery in a classroom experiment to its role in powering the modern world, electromagnetism has reshaped human civilization. Its principles underlie everything from the light in our homes to the intricate workings of electronic devices and even our understanding of the cosmos. Today, we continue to build upon the legacy of Ørsted, Faraday, and Maxwell. Advances in quantum electrodynamics, QED, a theory that combines quantum mechanics and electromagnetism, have led to deeper insights into particle interactions. As we continue to explore the mysteries of electromagnetism, it's clear that this force, fundamental to our universe, will continue to drive scientific and technological innovation for generations to come. Rutherford's gold foil experiment. In the early 20th century, physicists were striving to understand the structure of the atom, a question that had puzzled scientists for centuries. The prevailing model was known as the plum pudding model, proposed by J.J. Thomson after his discovery of the electron in 1897. According to this model, the atom was thought to be a sphere of positive charge with negatively charged electrons embedded within it, like raisins in a pudding. However, this model would soon be challenged by an experiment that became one of the most pivotal in modern physics, Ernest Rutherford's gold foil experiment. The early 1900s was an era of exploration in atomic theory. Scientists knew atoms contained both positive and negative charges, but they didn't know exactly how these were arranged. Thomson's plum pudding model, though widely accepted, lacked solid experimental backing and left many questions unanswered. Was positive charge evenly spread across the atom? How were electrons arranged? And what kept atoms stable? In 1909, Ernest Rutherford, a physicist from New Zealand working at the University of Manchester, set out to investigate these mysteries. Rutherford was a student of atomic structure, deeply curious about the forces within an atom. He and his students, Hans Geiger and Ernest Marsden, designed a simple but ingenious experiment that would change atomic theory forever. The experiment Rutherford, Geiger, and Marsden devised involved firing a beam of positively charged particles, alpha particles, at an extremely thin sheet of gold foil. Alpha particles, which consist of 2 protons and 2 neutrons, are positively charged and relatively heavy compared to electrons. They were chosen for their high energy and the fact that they could penetrate thin materials, allowing them to pass through the foil with minimal interaction, at least according to the predictions of the plum pudding model. If Thomson's model were correct, the alpha particles should pass almost straight through the foil, perhaps being slightly deflected by the pudding of positive charge in the atom. After all, in Thomson's view, the positive charge was weakly distributed throughout the atom, offering little resistance to the alpha particles. To detect the path of these particles, Rutherford's team used a screen coated with a zinc sulfide layer, which would flash when struck by an alpha particle. By observing the pattern of flashes on this screen, they could determine the paths of the alpha particles as they passed through or bounced off the gold foil. The results were both astonishing and puzzling. Most of the alpha particles did indeed pass through the foil with minimal deflection, just as the plum pudding model would predict. However, a small number of particles were deflected at large angles, some even rebounding almost straight back toward the source. This unexpected observation left Rutherford astonished. In his own words, he later remarked that it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The plum pudding model could not explain such large deflections. There had to be something much more concentrated within the atom that was strong enough to repel the alpha particles. Rutherford concluded that the atom's positive charge was not spread out evenly, as Thomson had suggested. Instead, it was concentrated in a very small, dense center, which he called the nucleus. The nucleus, Rutherford realized, contained nearly all the mass of the atom and carried a positive charge strong enough to repel the alpha particles that came close to it. The rest of the atom, Rutherford inferred, was mostly empty space, with electrons orbiting around this central nucleus. This was a radical shift from the idea of a pudding filled with positive charge to a structured model in which electrons moved around a dense core. This nuclear model of the atom not only explained the deflection patterns observed in the experiment, but also laid the groundwork for the planetary model of the atom, where electrons orbit a central nucleus in a manner similar to planets orbiting the Sun. Rutherford's model transformed our understanding of atomic structure. His discovery of the nucleus paved the way for future developments in atomic theory, including Niels Bohr's model of the atom, which introduced quantized electron orbits and further explained atomic stability. Rutherford's work was also foundational for the field of nuclear physics in 1917. He became the first to successfully split the atom, identifying the proton as a fundamental particle within the nucleus. Beyond atomic theory, Rutherford's findings reshaped our understanding of matter itself. The idea that atoms are mostly empty space was startling. It revealed that the solidity we perceive in matter is largely an illusion, a result of electromagnetic forces and not a packed mass of particles. This concept would later inform quantum mechanics, as scientists sought to understand the forces that govern subatomic particles. In retrospect, Rutherford's experiment was elegantly simple, yet it yielded insights that were anything but. By challenging the prevailing assumptions of his time, Rutherford uncovered one of the fundamental structures of the natural world. His discovery of the nucleus and the new atomic model didn't just update the scientific picture of the atom, it revolutionized physics, influencing everything from chemistry to quantum mechanics. The gold foil experiment is often celebrated not just for its groundbreaking findings, but also for its exemplary scientific approach. It showed how a well-designed experiment could dismantle established ideas and lead to a paradigm shift. Rutherford, with his open-minded interpretation and willingness to question accepted theories, set a high standard for scientific inquiry. In the end, Rutherford's work exemplifies the spirit of discovery, an experiment that seemed straightforward at the outset but yielded answers to some of the deepest questions about the structure of matter. His insights continue to shape our understanding of the atomic world and underscore the power of curiosity-driven science. Discovery of the electron. In the late 19th century, scientists were closing in on one of the most important discoveries in the history of physics, the electron. Before its discovery, the structure of the atom was a mystery. Many believed it was indivisible, the smallest building block of matter. This belief stemmed from ancient Greek philosophers, particularly Democritus, who had coined the term atom from the Greek word atomos, meaning uncuttable or indivisible. However, as experimental techniques advanced, scientists began finding clues that hinted at the atom's complexity, and the story of the electron's discovery would become a pivotal moment in unraveling that complexity. The journey to the electron's discovery begins with experiments on cathode rays. In the mid-1800s, scientists were fascinated by a strange phenomenon that occurred in vacuum tubes. When a high voltage was applied across two electrodes in a partially evacuated glass tube, a mysterious glow would appear inside. These glowing rays, known as cathode rays, seemed to flow from the negative electrode, or cathode, toward the positive electrode, or anode. Yet, the nature of these rays puzzled scientists. Were they particles, or were they waves of some kind? A series of experiments conducted throughout the late 19th century revealed that these rays could be deflected by magnetic and electric fields, which hinted at a particle-like nature. However, the scientific community remained divided, with some believing that cathode rays were a new type of wave, similar to light, and others arguing they were composed of particles. It was J.J. Thomson, an English physicist, who would solve this mystery. In 1897, Joseph John Thomson set up a series of experiments at the Cavendish Laboratory in Cambridge to analyze cathode rays more precisely. Thomson was determined to find out if cathode rays were indeed particles, and if so, what kind of properties they had. Using a specialized cathode ray tube that allowed him to apply both an electric and a magnetic field to the rays, Thomson was able to measure how the rays were deflected in each field. This setup was crucial. By adjusting the strength of the electric and magnetic fields until the deflection of the cathode rays canceled out, Thomson could calculate the ratio of the particle's charge to its mass, known as the charge-to-mass ratio, EEM. His measurements revealed that these particles were roughly 1,800 times lighter than a hydrogen atom, the lightest atom known. This was astounding. No one had ever imagined that there could be particles so much smaller than atoms. From his experiments, Thomson concluded that cathode rays were composed of particles that were far smaller than any atom and carried a negative electric charge. This discovery was revolutionary because it contradicted the idea that atoms were indivisible. Thomson had not only demonstrated that atoms could indeed be split into smaller parts, but he had also discovered the very first subatomic particle, which he named the electron. To help explain his findings, Thomson proposed a new model of the atom. Since he had observed negatively charged electrons, he reasoned that atoms must also contain positive charge to balance out the negative charge of the electrons. This led to the creation of the plum pudding model, in which an atom was envisioned as a pudding of positive charge, with negatively charged electrons embedded within it like plums in a dessert. Although the model was ultimately replaced by later discoveries, it represented a major step forward in understanding atomic structure. The discovery of the electron had immediate and profound implications. By proving that atoms contained even smaller particles, Thomson had opened the door to an entirely new realm of science, subatomic physics. The existence of electrons challenged scientists to rethink the nature of matter itself and raised new questions. If atoms contained electrons, where was the positive charge located? How were electrons arranged within atoms, and what held these particles together? Thomson's work also inspired a new generation of scientists. The quest to understand atomic structure became a central focus in physics, leading to groundbreaking work by Ernest Rutherford, who later identified the atomic nucleus, and Niels Bohr, who proposed a model of the atom that incorporated quantum mechanics. Moreover, the discovery of the electron had immediate applications. Electronics, as a field, owes its origins to Thomson's discovery, as understanding the behavior of electrons laid the groundwork for the development of transistors, semiconductors, and computing today. Nearly every piece of technology, from smartphones to medical imaging devices, relies on principles first glimpsed through the study of the electron. Reflecting on the discovery of the electron, it's remarkable how much impact a single breakthrough can have on science and society. Thomson's meticulous experiments showed how careful observation and a willingness to challenge accepted ideas could redefine our understanding of the universe. The electron's discovery marked the beginning of quantum theory and modern atomic physics, setting science on a course that would lead to some of the most profound advancements of the 20th and 21st centuries. In many ways, Thomson's work epitomizes the spirit of scientific discovery. He took what appeared to be a simple phenomenon, a glowing ray in a glass tube, and pursued it relentlessly, even when it defied the understanding of the time. Today, every time we flip a light switch, send an email, or use a computer, we are indirectly benefiting from Thomson's dedication to unraveling the mysteries of the electron. And so, with his discovery, J.J. Thomson didn't just identify a new particle. He forever changed the way we understand the fabric of matter and paved the way for the atomic age. Theory of Relativity. The story of the theory of relativity begins at the dawn of the 20th century, a time when science was beginning to challenge the very foundations of classical physics. For centuries, Isaac Newton's laws had dominated our understanding of motion, gravity, and the cosmos. But as scientists peered deeper into the workings of the universe, they discovered strange and perplexing phenomena that Newton's framework couldn't fully explain. The man who would rewrite the laws of space and time and change the course of science forever was Albert Einstein. Before Einstein, the scientific world had a well-accepted view of space and time, thanks to the works of Newton. His laws seemed to govern everything from the fall of an apple to the motion of planets. Space was considered to be a static, unchanging stage, and time was thought to flow at a constant rate everywhere. But something began to unravel this neat picture in the late 1800s and early 1900s, the behavior of light. In 1865, James Clerk Maxwell, a Scottish physicist, had formulated the equations that describe electromagnetic waves, including light. According to Maxwell, light was a form of energy that traveled in waves. More importantly, these waves were self-sustaining electric and magnetic fields created and propagated each other, traveling through space at a constant speed of about 299,792 kilometers per second. the speed of light, symbolized as c. This idea that light had a fixed speed regardless of the observer's motion was deeply puzzling. The Michelson-Morley experiment in 1887, which tried to measure the speed of light in relation to a supposed medium called the ether, a hypothetical substance thought to carry light waves, had failed to detect any difference. It seemed that no matter how fast the Earth was moving through space, the speed of light remained constant. This observation shook the foundation of classical physics. Enter Albert Einstein. Born in 1879, Einstein was an unconventional thinker who saw the world of physics not just through equations, but through thought experiments. He was inspired by the strange behavior of light and the mysteries of the ether. Instead of accepting the idea of ether or sticking with Newtonian physics, Einstein had a radical idea. What if space and time themselves were not fixed and absolute? What if they were dynamic, malleable, and could stretch or shrink, depending on the conditions of the universe? This was the birth of special relativity. In 1905, at the age of 26, Einstein published a paper titled On the Electrodynamics of Moving Bodies, in which he proposed his theory of special relativity. He suggested two simple but profound ideas that would change everything. 1. The laws of physics are the same for all observers, no matter how fast they are moving. Whether you are standing still, walking, or riding a train, the physical laws, like the rules governing light and motion, don't change. 2. The speed of light is constant for all observers, no matter how fast they are moving relative to the light source. This was a stunning idea. The concept that the speed of light is the same for everyone, regardless of their motion or the motion of the light source, shattered the old understanding of space and time. Under Newtonian physics, we would expect that if you were moving toward a light source, you'd measure the speed of light as faster than someone who was moving away from the source. But Einstein's theory said that light speed didn't change. It was the same for everyone, no matter how they moved. The consequences. Time and space are not what they seem. Einstein's breakthrough in special relativity also introduced an entirely new way of thinking about space and time. If time and space were fixed, they were easily understood and predictable. But in Einstein's world, space and time were interconnected. They were not absolute, unchanging entities. They were fluid. The concept of space-time was born, and ideas that fused the three dimensions of space, length, width, and height, with the dimension of time into a four-dimensional continuum. This realization had far-reaching consequences. One of the most famous results of special relativity is time dilation, the idea that time moves slower for objects that are moving near the speed of light. Imagine you were on a spaceship traveling at 99% the speed of light. If you traveled for what seemed like 1 year to you on the ship, you would return to Earth to find that many years had passed on Earth. The faster you move, the more your time slows down compared to someone who is standing still. Tianyin. Another remarkable result was length contraction. As objects move faster and approach the speed of light, their length in the direction of motion seems to shrink. An astronaut traveling near the speed of light might look at a stick of normal length and find that it appears to shrink when viewed from the perspective of someone on Earth. The grand leap, general relativity, and gravity. Einstein didn't stop with special relativity. In 1915, he introduced general relativity, a broader theory that included gravity, something special relativity didn't address. Before Einstein, gravity was understood as a force, as described by Newton's law of gravitation. But Einstein showed that gravity wasn't just a force. It was a result of the warping of space-time by mass. Imagine space-time as a stretched-out rubber sheet. If you place a heavy ball in the center, it causes the sheet to sag around the ball. This is how massive objects like stars or planets warp space-time. Smaller objects like planets or satellites move along these curves, which we experience as the force of gravity. For the first time, gravity was understood not as an invisible force acting at a distance, but as a bending of the very fabric of the universe itself. The legacy of relativity. Einstein's theory of relativity had profound implications for both physics and our view of the universe. It was confirmed through experiments like the bending of light around the sun during a solar eclipse, which was observed by Arthur Eddington in 1919. The results matched Einstein's predictions exactly. Today, relativity forms the cornerstone of modern physics. GPS satellites, for example, must account for time dilation effects predicted by Einstein's theory to provide accurate positioning data. Without relativity, the world of modern technology, and even our understanding of the universe, would be unrecognizable. The theory of relativity didn't just revolutionize physics. It changed the way we think about time, space, and reality itself. It showed us that the universe is far more complex and stranger than we ever imagined, forever altering our perspective of the world around us. The photoelectric effect. The photoelectric effect is one of the cornerstones of quantum physics, and it marks a pivotal moment in the journey toward understanding the strange and counterintuitive world of subatomic particles. In the early 20th century, physicists were already puzzled by some phenomena that didn't quite fit into the classical framework of physics. Among these anomalies was the way light interacted with metals to release electrons, a phenomenon that seemed to challenge everything physicists thought they knew about light. Enter Albert Einstein, whose work on the photoelectric effect would not only solve this mystery, but also lay the foundation for the quantum revolution. To understand the significance of the photoelectric effect, we first need to understand what was going on in the world of physics at the time. In the 19th century, light was traditionally thought of as a wave. This wave theory of light was beautifully explained by James Clerk Maxwell, whose equations showed that light was an electromagnetic wave traveling through space as oscillating electric and magnetic fields. This wave theory worked perfectly to explain many phenomena, from the bending of light around objects to the colors seen in a rainbow. But something curious began to happen when light interacted with metal surfaces. Scientists had observed that when light of a certain frequency was shone onto a metal surface, electrons were emitted from the metal. This was called the photoelectric effect. In theory, according to classical physics, this should have been a simple process. The wave-like nature of light suggested that if the light's intensity, brightness, was increased, the energy of the waves should also increase. Therefore, it was expected that brighter light would knock electrons out of a metal surface more effectively, regardless of the frequency of the light. However, experiments showed a surprising result. The energy of the emitted electrons did not depend on the brightness of the light. Instead, the light had to have a certain minimum frequency called the threshold frequency before any electrons were ejected. Once the frequency was above this threshold, the energy of the emitted electrons increased with the light's intensity, but only if the frequency was high enough. This was a major puzzle. If light were indeed just a wave, as classical physics suggested, the results didn't make sense. Why was the frequency, not the intensity, so crucial for the emission of electrons? This is where Albert Einstein entered the picture in 1905 in a paper that would forever change the course of physics. Einstein proposed a radically new idea. Light could also behave as if it were made of particles. These particles, which he called quanta, later known as photons, carried energy that was proportional to the frequency of the light. Einstein argued that when light hits a metal surface, it is the individual photons, not the overall wave of light, that transfer their energy to the electrons. If a photon has enough energy, that is, if its frequency is above the threshold, it can knock an electron loose from the metal's surface. If the photon's energy is less than the threshold, it will not have enough power to eject an electron, no matter how bright the light is. In classical wave theory, the intensity of light is linked to the amplitude of the wave. The greater the intensity, the more energy the wave carries, and thus more electrons should be ejected, regardless of the light's frequency. But Einstein's explanation turned this view upside down. With his particle theory of light, it wasn't the intensity that mattered, but the frequency. A bright light of low frequency still wouldn't have enough energy per photon to release an electron, no matter how many photons it had. Only high-frequency light, like ultraviolet light, contained photons with enough energy to knock electrons loose. This was a key insight that would eventually lead to the development of quantum mechanics, a field of physics that governs the behavior of particles at the smallest scales. Einstein's work showed that energy, light, and matter were not as separate as they once seemed. Instead, light could behave both as a wave and a particle, depending on the situation, a principle known as wave-particle duality. Einstein's explanation of the photoelectric effect was groundbreaking, but it wasn't immediately accepted by all scientists. The notion that light could act as both a wave and a particle was difficult for many to grasp, as it contradicted centuries of established thinking. However, the experimental evidence was undeniable. Einstein's work on the photoelectric effect was confirmed by numerous experiments, and in 1921, he was awarded the Nobel Prize in Physics for his contributions to our understanding of light. This discovery had far-reaching consequences. It not only helped to establish the theory of quantum mechanics, but also provided a clear demonstration of the quantization of energy, the idea that energy comes in discrete packets rather than being continuous. This idea would later extend to the behavior of atoms, electrons, and other subatomic particles. Furthermore, the photoelectric effect provided practical applications in technology. The phenomenon is the basis for devices such as solar cells, which convert sunlight into electricity, photodetectors, and light sensors, all of which rely on the interaction of light and matter in ways that Einstein helped explain. The photoelectric effect wasn't just an isolated phenomenon. It was a key piece of the puzzle that allowed scientists to understand the nature of light, energy, and matter at the deepest level. Einstein's work on the photoelectric effect remains one of the most important contributions to modern physics, showing us that light has a dual nature and laying the foundation for the quantum world that would be developed in the decades following his discoveries. In a sense, the photoelectric effect is a window into the quantum world where the rules are very different from our everyday experience. It's a world where particles can act like waves, energy comes in discrete packets, and time and space themselves become malleable. And it all started with a simple yet profound question about the nature of light and how it interacts with matter, questions that continue to shape the way we explore and understand the universe today. Quantum mechanics. In the early 20th century, physicists found themselves on the brink of an extraordinary breakthrough. Classical physics, with its elegant laws governing motion, gravity, and electricity, had done a remarkable job of explaining the world around us. Yet, as scientists peered deeper into the realm of the very small, the behavior of matter began to defy these well-established laws. The minute particles that made up atoms and molecules didn't behave like anything we had observed before. Atoms didn't follow the predictable paths classical physics suggested. Instead, these particles seemed to exist in a strange, fluctuating world, governed by rules that were far from intuitive. This strange new world would come to be called quantum mechanics. The seeds of quantum mechanics were first sown in the late 19th century, with the study of blackbody radiation. Scientists were trying to understand how objects like metal rods emitted radiation when heated. Classical physics suggested that objects at high temperatures should emit an endless amount of energy in a rainbow of wavelengths. Yet experiments showed that only certain wavelengths were emitted, and the amount of energy emitted at each wavelength was sharply limited. This was known as the ultraviolet catastrophe, a paradox that classical physics couldn't explain. The breakthrough came in 1900 when Max Planck, a German physicist, proposed a radical idea. Planck suggested that energy wasn't emitted in a continuous stream, but rather in discrete packets, or quanta. This was the first crack in the armor of classical physics. Planck's idea introduced the concept of quantization, the idea that energy, at the smallest scale, exists in discrete quantities. Though Planck's work solved the blackbody radiation problem, it was seen as a mathematical trick to avoid the paradox rather than a fundamental shift in understanding. Just 5 years later, in 1905, Albert Einstein took Planck's idea a step further. Einstein, in his study of the photoelectric effect, proposed that light, which had been treated as a wave, also had a particle-like nature. He suggested that light was composed of discrete packets of energy, which he called photons. When light struck a material, the photons would transfer their energy to electrons, knocking them free from the material's surface, much like how balls of energy might knock particles loose from a surface. Einstein's work showed that light behaved both like a wave and a particle, depending on the situation. This became the wave-particle duality. His explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921 and laid the groundwork for the quantum revolution. Light wasn't just a wave, and it wasn't just a particle. It was something in between, depending on how we observed it. But it wasn't just light that needed a new explanation. By the 1920s, physicists were finding that atoms themselves weren't behaving according to classical physics. The idea of atoms as tiny billiard balls following well-defined orbits around the nucleus was being shattered. Niels Bohr in 1913 proposed a new model of the atom based on quantized energy levels. In Bohr's model, electrons orbit the nucleus at certain discrete distances and could only gain or lose energy by jumping between these orbits. This idea was revolutionary. It explained why atoms emitted light only at specific wavelengths, and it introduced the idea that matter, too, might exhibit quantum properties. But the most famous contributions to the development of quantum mechanics came in the mid-1920s, when several physicists, including Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, contributed to the formal development of quantum theory. In 1925, Heisenberg developed matrix mechanics, a mathematical framework that described the behavior of particles in terms of observable quantities like position and momentum. His work was groundbreaking, but it didn't provide a clear picture of what was happening at the quantum level. Just a year later, Schrödinger developed his famous wave equation, which treated particles as waves rather than solid objects. The equation was a significant advance. It allowed physicists to predict where a particle might be, though it only gave probabilities, not certainties. The key insight of quantum mechanics was that particles, like electrons, didn't have definite positions or speeds until they were measured. Before being observed, particles existed in a superposition of all possible states as waves of probability. When a measurement was made, the wave of possibilities collapsed and the particle was found at a specific position. This fundamental uncertainty was formalized by Heisenberg's uncertainty principle, which stated that we cannot know both the position and momentum of a particle with absolute certainty at the same time. What quantum mechanics revealed was a world utterly unlike anything we could observe with our senses. At the quantum level, particles could exist in multiple states at once, superposition, be instantly connected across vast distances, entanglement, and move in ways that seemed to defy classical logic. But perhaps most surprisingly, these strange behaviors were not the result of flawed experiments or theoretical mistakes. Rather, they were the very nature of reality itself, shaped by the probabilistic laws of quantum mechanics. The key to understanding this new reality lies in the idea that at very small scales, the rules we take for granted in the macroscopic world, like certainty, continuity, and determinism, don't apply. Instead, probability and uncertainty take center stage. The behavior of particles can only be predicted in terms of the likelihood of finding them in particular states, not with certainty. In fact, many of the principles that define the quantum world, like the wave-particle duality, superposition, and entanglement, are so strange that they challenge our basic understanding of reality. Quantum mechanics opened up a new way of thinking about the universe and led to the development of countless modern technologies, including transistors, lasers, and even the computer you are using right now. But it also raised deeper philosophical questions. If particles exist in superpositions, how can they choose which state to be in when measured? If particles are entangled, does that imply some form of communication faster than the speed of light? These mysteries continue to shape the study of quantum mechanics today. But one thing is certain: quantum mechanics has completely reshaped our understanding of the universe at its most fundamental level. It's not just a set of mathematical formulas. It's a radically new way of understanding the nature of reality itself. In conclusion, quantum mechanics is one of the most successful theories in all of science. It has been tested and confirmed in countless experiments, and its implications continue to drive advancements in technology and our understanding of the universe. While the quantum world may seem strange and unfathomable, it is, at its heart, a world governed by fundamental principles that describe everything from the smallest particles to the entire cosmos. It is, in essence, the rule book for the universe at its most microscopic level. The uncertainty principle, Imagine you're at a concert trying to capture a perfect moment on your camera. You aim the lens and focus carefully on the stage, trying to capture a musician in action. As you get the perfect shot, something unexpected happens. The musician starts to move just as you click the shutter. The moment is blurry, and the motion isn't clear in the photograph. Now, imagine the opposite. If you had zoomed out to capture the full stage and froze the shot, the musician might be perfectly still, but the moment's detail is lost. The more you focus on one detail, position or movement, the more you lose track of the other. In a sense, this experience is not unlike a fundamental property of the quantum world, a concept known as Heisenberg's uncertainty principle. Just as in photography, where the clarity of one aspect comes at the cost of another, quantum particles, like electrons, cannot have both their position and momentum precisely measured at the same time, no matter how advanced our tools get. This principle, discovered by Werner Heisenberg in 1927, challenges our intuitive understanding of measurement and observation at the microscopic scale. To understand the development of this principle, let's step back to the 1920s. By this time, quantum mechanics was rapidly developing. Scientists like Niels Bohr, Erwin Schrödinger, and Werner Heisenberg had laid out the early foundations of quantum theory. In this new framework, particles like electrons were no longer seen as simple solid objects, but as quantum waves, existing in a probability cloud of different possible locations and energies. These particles could behave like both particles and waves, depending on the situation. A bizarre realization that shook the very foundation of classical physics. Heisenberg's contribution came when he was grappling with the complexities of quantum behavior. He was searching for a way to reconcile the behavior of particles and waves in a consistent way. At the time, Heisenberg had been studying the interactions between light and electrons, especially when light interacted with the electrons in an atom. The more precisely you tried to measure the position of an electron, the more uncertain its momentum, how fast it was moving and in which direction, became, and vice versa. This observation led Heisenberg to propose that there was a fundamental limit to how precisely certain pairs of physical properties could be measured at the same time. The uncertainty principle was born out of this realization. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Heisenberg's insight into this idea was not just philosophical, it had a mathematical foundation. This equation describes the precise relationship between the uncertainty in the position of a particle and the uncertainty in its momentum. The more precisely you measure one, the greater the uncertainty in the other. At first glance, this might seem like an experimental flaw, a limitation of our tools, but Heisenberg's point was much deeper. It was not a problem of measurement, but a fundamental aspect of nature itself. In the quantum world, uncertainty wasn't just a limitation of technology, it was built into the fabric of reality, a quantum challenge to determinism. Before Heisenberg's discovery, classical physics was grounded in the idea of determinism. Determinism states that if we know the position and velocity of a particle at one moment in time, we can predict where it will be in the future. It was a comforting, predictable worldview where everything from the motion of planets to the flight of a baseball could be understood through precise measurements and formulas. However, in the quantum world, Heisenberg's principle shattered this deterministic view. The behavior of quantum particles could no longer be described with the same certainty. The notion that we could know both the exact position and momentum of a particle at the same time was simply false. Instead, we had to embrace a new philosophy. Quantum mechanics was inherently probabilistic. Rather than precise trajectories, quantum particles exist in a cloud of probabilities, only becoming defined when we measure them. This uncertainty wasn't just due to our lack of knowledge. It was an inherent property of the quantum world. The philosophical implications. The uncertainty principle raised profound questions not only about physics, but also about the nature of reality itself. Could there ever be a point where we could know everything about a system, its position, velocity, energy, and more? The answer, according to Heisenberg, was a resounding no. This led to a shift in how physicists and philosophers viewed the act of measurement. In classical physics, measurement was seen as passive. We simply observe the system without affecting it. But in the quantum world, the very act of measurement influences the system. The particle's wave-like nature collapses into a specific position or momentum only once we measure it, and in doing so, we lose all other potentialities. This led to the Copenhagen interpretation of quantum mechanics, championed by Niels Bohr and Werner Heisenberg. According to this view, reality at the quantum level is not fixed until it is observed. Until we measure it, a particle exists in a superposition of all possible states. Once we observe it, it chooses a specific state. But the uncertainty principle ensures that this choice comes with a trade-off between position and momentum, everyday life, and the uncertainty principle. While the uncertainty principle might seem like an abstract concept far removed from daily life, it has practical implications in our modern world. The principle is behind the phenomenon of quantum tunneling, where particles pass through barriers that they classically shouldn't be able to. This principle is the reason why some technologies, like semiconductors and MRI scanners, work. The behavior of electrons in semiconductors is governed by the uncertainty principle, which allows modern electronics to function. Though the uncertainty principle challenges our classical intuitions about the universe, it has been validated countless times through experiments. It is a cornerstone of quantum mechanics and has had profound effects on technology, philosophy, and even our understanding of the universe. By showing us that there is a limit to our knowledge of the quantum world, Heisenberg revealed a deeper truth. Uncertainty is not just an inconvenience, but a fundamental feature of reality. Conclusion: the uncertainty principle doesn't just shape how we look at particles and waves, but it fundamentally changes our understanding of knowledge itself. It suggests that there are limits to what we can know about the universe. As technology advances and quantum mechanics continues to evolve, these principles will remain at the heart of our quest to understand the very nature of reality. Through uncertainty, we learn that there is beauty in the mystery, and sometimes the greatest discoveries come from embracing what we cannot fully know. Quantum entanglement. Imagine two friends separated by thousands of miles, yet when one of them laughs or cries, the other instantly knows. This seemingly magical link, one that defies distance and logic, resembles a concept in quantum physics known as quantum entanglement, discovered in the early 20th century. Entanglement has been famously described by Albert Einstein as spooky action at a distance. Despite sounding mystical, quantum entanglement is one of the most verified and compelling phenomena in quantum mechanics, a phenomenon that challenges our very understanding of space, time, and reality. The roots of quantum entanglement date back to the early 20th century, during the infancy of quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment, now famously known as the EPR paradox. Einstein-Podolsky-Rosen paradox. At the time, Einstein was skeptical of quantum mechanics. He couldn't reconcile the inherent randomness and uncertainty of quantum theory with his belief in a predictable, orderly universe. Einstein and his colleagues suggested that if quantum mechanics were correct, it implied the existence of strange, non-local connections between particles. In other words, two particles could be linked in such a way that the state of one particle would instantaneously influence the state of another, no matter how far apart they were. They believed this spooky action at a distance hinted at a flaw in quantum mechanics. For them, this paradox was a way of highlighting the theory's incompleteness, suggesting there must be hidden variables that explained the behavior in a more classical, predictable way. Then, in the 1960s, John Bell, an Irish physicist, took Einstein's challenge seriously. Bell devised a mathematical framework called Bell's theorem, which allowed scientists to test the validity of quantum mechanics versus Einstein's hidden variable theory. His theorem showed that if quantum mechanics was correct, there would be measurable differences in the statistical correlations between entangled particles compared to any classical theory. In the following decades, several experiments tested Bell's theorem, most famously those led by physicist Alain Aspect in the 1980s. Each experiment confirmed that quantum mechanics held true. Entangled particles did indeed behave as if they were instantaneously connected, regardless of the distance between them. These results defied any classical explanation and solidified entanglement as a fundamental aspect of quantum mechanics. Quantum entanglement is a unique relationship between two or more particles in which the particles become linked, such that the state of one particle directly influences the state of the other, no matter the distance between them. If one particle's properties are measured, the properties of its entangled partner are determined immediately, even if it's all on the other side of the universe. To understand this more intuitively, let's imagine flipping two coins that are somehow quantum entangled. Normally, if we flip two coins, we'd expect independent results. One coin might land heads while the other might land tails. However, with entangled coins, every time you flip one coin and observe its outcome, the other coin instantly shows the opposite result, as if they communicate with each other instantaneously. No matter where these coins are located, whether in your hand or across the galaxy, the link between them holds. In quantum terms, this means if two particles, such as electrons or photons, are entangled, they share a quantum state. The state of one particle is mirrored in the other. For example, if two photons are entangled, and you measure one photon to have a certain polarization, say vertical, the other photon's polarization will instantaneously align in a complementary way, regardless of the physical distance separating them. Entanglement defies classical logic because, according to the theory of relativity, information or influence shouldn't be able to travel faster than the speed of light. In entanglement, however, the changes appear to be instantaneous. This phenomenon seems to suggest that space, in some way, is an illusion, or at the very least, doesn't function as we intuitively understand it. The spooky connection between entangled particles suggests that, at a fundamental level, everything might be interconnected in ways that transcend traditional notions of locality. Although entanglement is strange and counterintuitive, it's far from being just a theoretical curiosity. Quantum entanglement has real-world applications, especially in the burgeoning field of quantum computing. Unlike classical bits that are either a 0 or a 1, quantum bits or qubits can exist in a state of 0, 1, or both simultaneously, thanks to a principle called superposition. Entanglement allows qubits to interact in complex ways, enabling quantum computers to perform calculations exponentially faster than traditional computers for certain tasks. Another exciting application is quantum cryptography, where entanglement can be used to create secure communication channels. With entangled particles, any eavesdropper attempting to intercept the particles would disturb the entanglement, revealing their presence immediately. This could pave the way for unbreakable encryption methods that provide unparalleled levels of security in communication. Entanglement also plays a role in emerging research on quantum teleportation. While it doesn't involve physically transporting objects as in science fiction, quantum teleportation allows the instantaneous transfer of quantum information from one location to another using entanglement. This has significant implications for data transfer and secure communication across vast distances. Quantum entanglement challenges our fundamental understanding of reality, sparking debate and philosophical discussions. The phenomenon raises questions about the nature of space and time, the limits of human knowledge, and the interconnectedness of the universe. Some physicists and philosophers speculate that entanglement could hint at a deeper, underlying reality, a type of hidden layer beneath the observable universe where everything is interconnected. The nature of this connection is still a mystery. Is there a hidden mechanism that links entangled particles, or is space itself, as we understand it, not as fundamental as it seems? Quantum entanglement encourages us to explore these ideas and consider possibilities that defy our current understanding of the universe. Quantum entanglement represents one of the most profound insights into the quantum world. Through the efforts of Einstein, Podolsky, Rosenbell, and countless experimental physicists, we've learned that the quantum world operates by rules that challenge classical physics and our very perception of reality. Entanglement suggests a universe more interconnected than we can imagine, a world where particles separated by immense distances still speak to one another instantaneously. It's a phenomenon that opens up questions about the fundamental structure of the universe, hinting at hidden layers and relationships that transcend our current understanding. In studying entanglement, we are reminded that reality is not as straightforward as it appears, and that, at its deepest level, the universe holds mysteries waiting to be unveiled. The Big Bang Theory. Imagine rewinding the history of the universe like a film, watching galaxies drift backward, stars collapse, and cosmic clouds of dust and gas condense into tight knots. This backward journey reveals a universe that once occupied an unimaginably small, dense, and hot point. This concept, the Big Bang Theory, is humanity's best scientific explanation for how the universe began and evolved. But this theory wasn't born in a flash. It took decades of debate, evidence, and serendipitous discoveries to piece it together. The story of the Big Bang Theory starts with Albert Einstein in the early 20th century. Einstein's Theory of General Relativity, published in 1915, described how gravity works on a cosmic scale, revealing that massive objects warp space and time around them. Yet, when applying his equations to the entire universe, Einstein was baffled. His equations seemed to suggest an expanding or contracting universe, which conflicted with the common belief at the time that the universe was static and unchanging. To align his theory with this steady-state idea, Einstein introduced a cosmological constant to force his equations into a model of a stable universe. Meanwhile, Georges Lemaitre, a Belgian priest and mathematician, saw something intriguing in Einstein's equations. In 1927, he proposed the bold idea that the universe wasn't static, but expanding. Lemaitre suggested that if we ran the universe's expansion backward, we'd reach a point where everything began, a primeval atom from which the universe burst into existence. At the time, this concept was radical and widely dismissed, even by Einstein himself. In the late 1920s, the American astronomer Edwin Hubble delivered groundbreaking observational evidence that would transform Lemaitre's hypothesis into a scientifically backed theory. Using the powerful telescopes at Mount Wilson Observatory, Hubble studied distant galaxies and found that they all appeared to be moving away from Earth. Even more astonishing, the farther a galaxy was, the faster it was receding. This phenomenon, now known as Hubble's law, pointed to an expanding universe. Hubble's observations showed that galaxies are not stationary, but are being pushed apart, suggesting that the universe itself is stretching. Hubble's findings gave credibility to the idea of a dynamic universe, yet the scientific community was divided. Skepticism remained, especially among those who held on to the idea of a steady-state universe, but evidence continued to pile up. One of the most compelling pieces of evidence for the Big Bang Theory came in the form of an unexpected discovery in the 1960s. Physicists Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, testing a large antenna built for satellite communications. However, their work was plagued by an annoying hum of static noise that seemed to come from every direction. They tried everything to eliminate the noise, even going as far as cleaning pigeon droppings off the antenna, but the hum persisted. As it turned out, Penzias and Wilson had accidentally detected something groundbreaking: cosmic microwave background, CMB radiation. This faint glow of radiation, now understood as the afterglow of the Big Bang, was the thermal remnant of the universe's fiery birth. The CMB is a snapshot of the universe at around 380,000 years old, when it had cooled enough for atoms to form and photons to travel freely through space. This discovery was monumental. It provided a fossil of the early universe and was the smoking gun that validated the Big Bang Theory. The Big Bang Theory describes an event around 13.8 billion years ago when the universe began as an incredibly hot, dense point, often called a singularity. For reasons still unknown, this singularity began to expand, setting off the process of cosmic evolution. In the first moments after the Big Bang, the universe was a seething mass of particles, protons, neutrons, electrons, all too hot and energetic to form atoms. As the universe continued to expand and cool, these particles eventually combined, forming hydrogen and helium, the first atoms. In the first few 100 million years, slight variations in the density of matter led to the gravitational collapse of gas clouds, which formed the first stars and galaxies. Over billions of years, galaxies merged, stars were born and died, and complex structures formed, leading to the universe we observe today. To grasp the concept of an expanding universe, imagine a balloon with dots on its surface. Each dot represents a galaxy. As you blow up the balloon, the surface expands and the dots move away from each other. This is similar to how galaxies recede from each other as space itself stretches, though unlike the balloon, the universe expands in 3 dimensions, with galaxies moving apart in every direction. Another useful analogy is to think of a loaf of raisin bread rising in the oven. As the dough, representing space, expands, the raisins, representing galaxies, move away from each other. Importantly, it's not that the raisins themselves are moving through the dough. Rather, the dough itself is expanding and carrying the raisins along with it. This expansion isn't happening within pre-existing space. The creation of space itself is the essence of the Big Bang. The Big Bang theory is the cornerstone of modern cosmology, providing a framework to understand the evolution of the universe from its infancy to today. Yet, as much as we know, many mysteries remain. Scientists still seek to understand what triggered the Big Bang. The theory also doesn't explain what happened before this event, or what lies beyond our observable universe. Additionally, discoveries in the late 20th and early 21st centuries, such as dark matter and dark energy, suggest that our understanding of the cosmos is incomplete. Dark matter, which doesn't emit or interact with light, seems to hold galaxies together, while dark energy is accelerating the universe's expansion. These components make up most of the universe, yet they remain largely mysterious, leading scientists to wonder if an even deeper, more comprehensive theory of the cosmos awaits discovery. The Big Bang theory stands as one of the most profound scientific insights into our origins. By observing the universe's expansion and listening to the cosmic hum of background radiation, scientists have pieced together a story that traces our existence back to an ancient, fiery beginning. This theory transforms the universe from a static backdrop into a dynamic, evolving entity with a beginning, a middle, and possibly an end. And while the Big Bang theory answers some of humanity's biggest questions, it leaves us with others, new frontiers for exploration, as we continue to seek the truth of our cosmic origins. The standard model of particle physics. Imagine if the universe were like an enormous Lego set, with each structure around us, stars, planets, humans, and even the air, constructed from tiny blocks, each with unique properties. The standard model of particle physics is like the instruction manual for these blocks, identifying the basic pieces that compose everything in the universe and the forces that hold them together. But the journey to this manual wasn't straightforward. It was the result of decades of groundbreaking experiments, brilliant theories, and an ongoing effort to decode the language of nature at its most fundamental level. The discovery of the standard model didn't happen in a single moment or by a single scientist. It began in the late 19th and early 20th centuries as physicists tried to make sense of the smallest components of matter. J.J. Thomson's discovery of the electron in 1897 showed that atoms were not indivisible, as once thought, but contained even smaller parts. Later, in 1911, Ernest Rutherford's gold foil experiment revealed the atomic nucleus, a dense center surrounded by electrons. These discoveries kicked off a wave of research that led to the realization that atoms were not fundamental at all. They were built from even tinier particles. Throughout the early 20th century, scientists uncovered several mysterious particles, and by the 1930s, the proton and neutron were identified as the building blocks of atomic nuclei. But these discoveries raised questions. Were protons and neutrons fundamental, or did they also contain smaller parts? What forces held them together? As physics progressed, quantum mechanics and special relativity laid the groundwork for understanding particles at tiny scales and high speeds. In the 1950s and 1960s, the development of particle accelerators Huge machines that could smash particles together at high speeds allowed scientists to observe phenomena they'd never seen before. Every collision seemed to reveal new particles, from pions to muons to strange quarks. There were so many new discoveries that physicists jokingly called it a particle zoo. It was during this particle explosion that scientists began looking for a unifying theory that could organize these particles and describe their interactions. This search led to the Standard Model, a theoretical framework combining three of nature's four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. One of the breakthrough ideas in the Standard Model came from Murray Gell-Mann in 1964, who proposed the concept of quarks. Quarks are elementary particles that combine to form protons, neutrons, and other particles known as hadrons. Just like letters in an alphabet can combine in various ways to form words, quarks combine in different combinations to form the particles we observe in nature. Gell-Mann initially proposed three types of quarks: up, down, and strange, which explained many of the particles scientists were observing. With quarks, the idea of a fundamental building block was revived, but there was more to understand. In the Standard Model, there are actually 6 types of quarks: up, down, charm, strange, top, and bottom. These quarks combine in various ways to make protons and neutrons, among other particles. Quarks are bound together by the strong force mediated by particles called gluons, which act as the glue holding quarks together inside protons and neutrons. The Standard Model also explains how particles interact through fundamental forces. Besides quarks, the Standard Model includes leptons, like the familiar electron, and force-carrying particles known as bosons. Each force has a corresponding boson that carries the force. For example, photons carry the electromagnetic force, allowing charged particles to interact. The W and Z bosons are responsible for the weak nuclear force, which governs radioactive decay. Gluons mediate the strong force that binds quarks together in atomic nuclei. These discoveries gradually came together to form the Standard Model, but one important piece was missing: mass. While the Standard Model successfully explained the fundamental particles and their interactions, scientists were puzzled about how particles acquire mass. In 1964, physicists Peter Higgs and others proposed the existence of a field, now called the Higgs field, which pervades all of space. Particles interacting with this field would acquire mass, similar to how a ball rolling through water moves slower than one rolling through the air. The existence of the Higgs field implied a new particle, the Higgs boson. For decades, the Higgs boson was theoretical. It had to be there according to the Standard Model, but no one had observed it. Finally, in 2012, the Large Hadron Collider, LHC, in Switzerland, provided enough energy to detect the Higgs boson, confirming a central prediction of the Standard Model. One way to understand the Standard Model is to imagine a huge, invisible web that connects everything in the universe. The web is made up of particles that interact with each other through exchanges of invisible messenger particles. For example, if you and a friend toss a ball back and forth, the ball can represent a force, say the electromagnetic force, and by throwing it, you're interacting. The Standard Model explains how particles toss these messengers, like photons or gluons, to experience forces. Another analogy is to think of quarks as building blocks that come in different flavors or types. Just as a sandwich could be made from different ingredients, particles like protons and neutrons are formed from different combinations of quarks, held together by gluons. This recipe of quarks, gluons, and force carriers forms the basis of everything around us. The Standard Model is remarkably successful, describing nearly every known particle interaction and enabling predictions that have stood up to experimental testing. However, it's not a complete theory. The model doesn't include gravity, and it doesn't explain dark matter and dark energy mysterious components that make up most of the universe's mass and energy. There's also the question of why there are precisely 6 quarks and 6 leptons, or why particles have the masses they do. The Standard Model of particle physics is a crowning achievement of modern science. encapsulating our understanding of the universe's fundamental particles and forces. It is the blueprint for the microcosmic world, capturing everything from the tiniest quarks to the interactions that shape the cosmos. And while it answers many questions, it leaves the door open to deeper mysteries, encouraging physicists to continue exploring, discovering, and refining the story of what our universe is made of and how it all fits together. Hawking radiation. Imagine black holes as cosmic monsters devouring everything that crosses their path, including light. For centuries, they were thought of as the ultimate cosmic traps. Once something fell into a black hole, it was gone forever. However, in the early 1970s, a young physicist named Stephen Hawking challenged this idea with a radical discovery. Black holes could actually emit energy, and over time, they could even disappear completely. This groundbreaking idea, known as Hawking radiation, transformed our understanding of black holes and raised profound questions about the nature of the universe. To understand how Hawking arrived at his theory, we need to look at the backdrop of the 20th century physics landscape, dominated by two seemingly incompatible theories: Einstein's general theory of relativity and quantum mechanics, general relativity, explains how massive objects warp the fabric of space and time, forming gravitational fields, while quantum mechanics describes the behavior of particles on an incredibly small scale. Yet, black holes challenge both theories, sitting at the intersection where gravity becomes so intense that quantum effects can no longer be ignored. In the early 1970s, Hawking, a young physicist at Cambridge University, began investigating the properties of black holes using these two theories. Black holes were thought to only grow by absorbing matter and energy, and were otherwise inert. But quantum mechanics hinted at something different happening at the event horizon, the boundary beyond which nothing, not even light, can escape. To develop his theory, Hawking turned to the strange, often counterintuitive world of quantum mechanics, particularly the idea of quantum fluctuations. In the quantum world, empty space isn't truly empty. It's a seething, energetic vacuum where pairs of particles and antiparticles spontaneously appear and annihilate each other. These particles typically pop into existence, interact briefly, and then disappear, leaving no trace behind. However, Hawking proposed that when these pairs of particles form near the event horizon of a black hole, something unusual might happen. Sometimes, instead of annihilating each other, one particle could fall into the black hole, while the other escapes into space. In this case, the escaped particle would appear as radiation, visible from a distance. This radiation escaping from the black hole became known as Hawking radiation. Hawking realized that as this radiation continued to be emitted, it would carry energy away from the black hole. Over time, this energy loss would cause the black hole to lose mass, a process known as black hole evaporation. If this process continues long enough, the black hole could, in theory, completely evaporate, disappearing into a burst of energy. This was a revolutionary concept. Before Hawking's work, black holes were thought to be eternal. Hawking radiation showed that black holes could actually die, fundamentally changing the way we think about these cosmic objects. It also suggested that black holes weren't just one-way traps. They had a way of releasing energy back into the universe. The discovery of Hawking radiation didn't just add a new chapter to black hole physics, it also forced physicists to confront deep questions about information in the universe. In quantum mechanics, information about the state of a system is preserved over time, meaning we could theoretically trace back the history of any particle. But if black holes could emit radiation and eventually evaporate, what would happen to all the information that fell into them? This paradox, known as the information paradox, has puzzled physicists for decades. If the information within a black hole is lost forever, it would contradict the principles of quantum mechanics. If it somehow survives, we would need new physics to explain how. To this day, scientists are still grappling with these questions, and the study of Hawking radiation remains a cornerstone of efforts to reconcile general relativity with quantum mechanics. Imagine a bustling city with a central recycling plant that never lets any waste escape. For years, it's believed that any item that goes into this plant is permanently destroyed. But then, a scientist discovers that, under certain conditions, some of the waste particles at the plant's edge actually escape. Even more astonishing, as these particles continue to escape, the recycling plant itself begins to shrink and eventually disappears. This surprising turn of events is analogous to Hawking's insight. Black holes, once thought to be cosmic traps, could actually lose mass over time through radiation and ultimately even cease to exist. Hawking's discovery of black hole radiation made him a celebrity in the physics world and beyond. It provided a glimpse into the quantum workings of black holes and brought physicists a step closer to understanding how the universe's most powerful forces interact. Today, Hawking radiation is considered one of the great theoretical breakthroughs of 20th century physics. It has inspired countless research efforts aimed at understanding black holes, quantum gravity, and the nature of space and time. Directly observing Hawking, radiation is practically impossible. The radiation is incredibly faint, far weaker than the cosmic background radiation left over from the Big Bang. For most black holes, the process of evaporation would take far longer than the current age of the universe. However, scientists have designed experiments on Earth to mimic aspects of Hawking radiation using analog systems like sound waves in certain materials, hoping these experiments will give insights into the behavior of black holes. Hawking radiation stands as a monumental leap in our understanding of black holes. It's a reminder that even the most mysterious entities in the universe aren't beyond human comprehension. Stephen Hawking's insight showed that black holes aren't eternal prisons, but dynamic objects that interact with the universe in complex ways. Through Hawking's discovery, we gained a clearer view of the cosmos and set the stage for future breakthroughs as scientists continue to explore the mind-bending mysteries of space, time, and the fundamental nature of reality. Superconductivity and superfluidity. In the early 20th century, as scientists began to experiment with temperatures close to absolute zero, the lowest possible temperature around minus 273.15 degrees Celsius or 0 Kelvin, they discovered strange and mysterious properties in materials that defied conventional physics. Two of the most intriguing phenomena they encountered were superconductivity and superfluidity. These effects, which occur in certain materials when they reach extremely low temperatures, opened up a new realm in physics and continue to inspire breakthroughs across science and technology. The story of superconductivity begins in 1911 with Dutch physicist Heike Kamerlingh Onnes at the University of Leiden. Onnes was a pioneer in the study of cryogenics, specializing in reaching ultra-low temperatures. In 1908, he became the first person to successfully liquefy helium, achieving temperatures just a few degrees above absolute zero. This achievement allowed him to test how materials behaved in such cold conditions. One of the key experiments Onnes conducted was on mercury, a familiar metal known to conduct electricity fairly well at room temperature. But as he cooled the mercury closer to absolute zero, something astonishing happened. At a temperature of 4.2 Kelvin, 268.95 degrees Celsius, the mercury's electrical resistance, the usual hindrance that causes energy loss in the form of heat, suddenly dropped to zero. In other words, the mercury allowed electric current to flow without any resistance at all. This was the first documented observation of superconductivity. To understand how groundbreaking this discovery was, consider an everyday analogy. Normally, when electricity flows through a wire, some energy is lost as heat because of resistance. This is like water flowing through a pipe with friction. Some of the water's energy dissipates as it rubs against the walls of the pipe. But superconductors are like perfectly frictionless pipes for electricity. In a superconductor, an electric current could theoretically flow forever without losing any energy. This property holds extraordinary potential for energy-efficient power grids, MRI machines, particle accelerators, and even maglev trains. But what exactly causes this strange effect? Scientists would spend decades unraveling the mystery of superconductivity. It wasn't until 1957 that American physicists John Bardeen, Leon Cooper, and Robert Schrieffer proposed the BCS theory to explain the phenomenon. They suggested that at ultra-low temperatures, electrons in a superconductor form pairs, called Cooper pairs, which move through the material in a coordinated manner that prevents energy loss from resistance. These pairs can slide through the atomic lattice of the material without being scattered, enabling zero resistance flow. Superfluidity, discovered a couple of decades later, shares an eerie resemblance to superconductivity, but with a twist. It occurs in liquids instead of solids. In the 1930s, Soviet physicist Pyotr Kapitsa and American physicists John Allen and Don Messener observed a startling behavior in liquid helium when it was cooled to 2.17 Kelvin. Below this temperature, liquid helium transitioned into a phase with zero viscosity, meaning it could flow without any resistance whatsoever. Kapitsa coined this phenomenon superfluidity. Imagine a glass of water where if you stirred it, the water would continue to spin indefinitely. This defies our everyday experience with fluids, which always lose energy due to friction and eventually come to a standstill. Superfluid helium, however, can climb up walls, seep through the tiniest of cracks, and maintain a perpetual flow in a closed loop without any external energy input. Superfluidity baffled scientists because it seemed to contradict all known laws of fluid dynamics. It turned out that this strange state of matter could be explained by quantum mechanics, particularly the idea of Bose-Einstein condensation. In simple terms, when helium atoms reach super-cold temperatures, they behave more like waves than particles, overlapping and moving in perfect harmony as a single quantum state. This collective behavior allows the helium atoms to flow without losing energy to viscosity. The discoveries of superconductivity and superfluidity have had profound effects on science and technology. Superconductors, for example, have made possible some of the most powerful magnets in existence. These magnets are used in MRI machines to generate high-quality images of the human body, and in particle accelerators like the Large Hadron Collider to probe the fundamental particles of the universe. The zero-resistance property also makes superconductors ideal for high-speed maglev trains, which can levitate and move without friction, potentially revolutionizing transportation. Superfluidity, while still more confined to theoretical and experimental realms, has had significant implications in understanding quantum mechanics and the behavior of matter at extreme conditions. The study of superfluid helium, in particular, has provided insights into quantum turbulence and has inspired the exploration of other exotic states of matter, such as Bose-Einstein condensate and atomic gases. Consider a regular liquid as a group of people walking through a crowded hallway. Each person must adjust their pace to avoid bumping into others, leading to an overall slow and chaotic movement. But in the case of a superfluid, it's as if all the people were suddenly in perfect harmony, gliding without any collisions, almost as if they were moving as one. This is similar to how atoms behave in a superfluid state, moving collectively without any friction. Similarly, for superconductors, imagine electrons in a conductor like cars on a busy road, where each car occasionally gets slowed down by bumps and turns, representing resistance. In a superconductor, however, all cars move in pairs, coordinated so perfectly that they encounter no obstacles and can drive endlessly without losing speed. This frictionless movement explains why superconductors are so remarkable. The discoveries of superconductivity and superfluidity opened a window into the strange, quantum-dominated world of ultra-cold physics, challenging our intuitions and broadening our understanding of matter. These phenomena not only demonstrate the fascinating behaviors that emerge at extremely low temperatures, but also provide valuable applications in technology and fundamental science. As scientists continue to experiment with these states, including efforts to achieve superconductivity at higher temperatures, the possibilities for energy efficiency, medical technology, and our grasp of the quantum world grow ever more promising. The Anthropic Principle. The Anthropic Principle is a philosophical framework that tries to answer one of the most profound questions humanity has ever asked. Why does the universe appear to be finely tuned for life? The term anthropic refers to humans, and the principle essentially asks, why our universe has the exact physical conditions that allow conscious beings to exist and observe it. Developed and formalized in the latter half of the 20th century, the Anthropic Principle has become a major topic in both physics and philosophy, influencing debates about cosmology, quantum mechanics, and even the existence of parallel universes. The story begins in the early 20th century when physicists began discovering the fundamental forces and constants that govern our universe, such as the speed of light, gravitational strength, and the charge of the electron. Physicists noticed that if any of these constants were even slightly different, the universe as we know it couldn't exist. Stars wouldn't form, atoms wouldn't bond, and life would be impossible. This led to a realization. Our universe seemed to be perfectly tuned for the existence of life, almost like a cosmic symphony where every note and pitch is precisely calibrated for harmony. Physicists in the 1960s and 1970s, including Brandon Carter, a British cosmologist, began to explicitly formulate what became known as the Anthropic Principle. Carter introduced this idea in 1973 during a conference celebrating the 500th birthday of Nicholas Copernicus. Carter argued that the universe's parameters aren't randomly configured. Instead, they appear biophilic, conducive to life. The Anthropic Principle comes in two main forms: the weak Anthropic Principle, WAP, and the strong Anthropic Principle, SAP. 1. Weak Anthropic Principle, WAP. This version simply states that the universe must have properties compatible with life because we are here to observe it. In other words, the fact that we observe a life-friendly universe is not surprising because if the universe didn't allow life, we wouldn't be here to notice. The weak Anthropic Principle is more of a tautology. It doesn't explain why the universe has these properties, only that it must, given our existence. 2. Strong Anthropic Principle, SAP. The strong Anthropic Principle goes a step further, suggesting that the universe's properties are not just accidentally compatible with life, but that they somehow require or are destined to produce observers. This implies a deeper reason behind the universe's design, almost hinting at purpose or intentionality, though this notion remains controversial. Imagine you walk into a kitchen and find a cake baking in the oven, filled with the exact ingredients that make it both delicious and structurally sound. This cake has the perfect amount of flour, sugar, eggs, and other ingredients to produce a fluffy and flavorful dessert. If any ingredient were slightly off, the cake would collapse or taste terrible. Now, you might wonder, why does this cake have the precise ingredients needed to make it delicious? The Anthropic Principle would suggest that the cake had to have these specific conditions. Otherwise, it wouldn't be there to be observed as a cake at all. In the same way, our universe appears to be made up of just the right ingredients to allow conscious beings to observe it. But why it has these ingredients is where the mystery deepens. In the late 20th century, the Anthropic Principle became a central point of discussion in physics and cosmology, especially as theories about the multiverse gained traction. The Multiverse Theory proposes that there might be an enormous or even infinite number of universes, each with its own unique set of physical laws and constants. In this framework, the Anthropic Principle can be explained by probability. Out of countless universes, we happen to be in one where the constants allow for life, just by chance. The Anthropic Principle has also played a crucial role in the development of string theory and quantum mechanics. Some interpretations of quantum mechanics, for instance, suggest that the universe doesn't settle into a single state until it is observed. This ties in intriguingly with the Anthropic Principle, as it implies that our observation has an active role in defining the universe's parameters. The Anthropic Principle has not been without controversy. Some physicists and philosophers argue that it's not really a scientific principle because it doesn't provide testable predictions. Rather, it seems more like a philosophical argument. Critics say it's a cop-out explanation for the universe's fine-tuning, avoiding the search for deeper underlying laws. Others, however, see it as an essential aspect of modern cosmology. Supporters argue that the Anthropic Principle helps prevent scientists from pursuing unnecessary explanations for phenomena that are merely preconditions for our existence. For example, instead of asking why the gravitational constant has its exact value, One could simply say, if it were different, we wouldn't be here to ask. In recent years, the Anthropic Principle has continued to inspire new scientific ideas. Physicist Leonard Susskind, a key proponent of the Multiverse Theory, has suggested that the Anthropic Principle could help explain the cosmological constant problem. The cosmological constant, which relates to the universe's expansion, is precisely tuned to a value that allows galaxies to form and life to develop. Susskind and others argue that the multiverse theory combined with the Anthropic Principle might explain why our universe has this exact value. Another notable figure, the British physicist Stephen Hawking, was both intrigued by and skeptical of the Anthropic Principle. He recognized its utility in understanding why the universe allows for life, but he was cautious about attributing purpose to the universe, preferring explanations that could be grounded in mathematical laws and physical theories. The Anthropic Principle remains one of the most compelling and debated ideas in modern science. By focusing on the conditions necessary for life, it challenges our understanding of the universe and prompts us to ask whether there is a deeper reason behind these conditions. Whether viewed as a tautology, a guiding framework, or a hint of purpose, the Anthropic Principle forces us to reflect on our place in the cosmos. It's a reminder that the universe, with its intricate symphony of laws and constants, is both comprehensible and profoundly mysterious. And perhaps, just perhaps, it's tuned for us to observe, question, and explore. String theory. String theory is one of the most ambitious ideas in physics, aiming to be a theory of everything that could reconcile quantum mechanics and general relativity, two of the most fundamental, yet fundamentally different frameworks in modern physics. In its essence, string theory suggests that the most basic elements of the universe are not particles like electrons or quarks, but tiny vibrating strings. Each string vibrates at a specific frequency, and the mode of vibration determines the properties of the particle it manifests as. It's as if the universe is an orchestra, with different instruments playing unique notes to create the complex melody of reality. String theory wasn't originally aimed at unifying physics. Its origins trace back to the 1960s, a time when physicists were wrestling with the mysteries of the atomic nucleus. In those days, they had discovered that particles called hadrons, like protons and neutrons, interacted in ways that were not fully understood. Italian physicist Gabriele Veneziano was exploring the unusual properties of these interactions when he stumbled upon a mathematical formula, later known as the Veneziano amplitude, that described the interactions of these particles surprisingly well. At the time, physicists didn't know why this formula worked. They only knew it seemed to describe reality accurately. It was in 1970 that Leonard Susskind, along with Holger Beck-Nielsen and Yoichiro Nambu, found that Veneziano's mathematical formula could be visualized as describing a one-dimensional vibrating string. This was a paradigm shift. Instead of particles being treated as dimensionless points, they were now conceived of as tiny loops or segments of strings that could vibrate in various ways. When these strings oscillate, they give rise to different particles, much like how a single guitar string can produce different notes based on how it's plucked or tuned. As physicists began exploring the implications of string theory, they realized it offered a remarkable and unique perspective. It had the potential to unify all fundamental forces under one framework. However, early versions of string theory had limitations and inconsistencies. For instance, they predicted not 3 but 10 dimensions of space and time, 6 more than what we experience. This initially seemed absurd, but physicists soon learned that these extra dimensions could be compactified or curled up so tightly that we wouldn't perceive them in our everyday reality. As the theory developed, physicists began to explore ways to extend it further, giving birth to superstring theory in the 1980s. Superstring theory introduced the concept of supersymmetry, a proposed symmetry between particles that carry forces, like photons, and particles that make up matter, like electrons. Supersymmetry added stability to the equations, allowing physicists to develop more consistent models. Superstring theory was powerful and elegant, unifying all 4 fundamental forces: gravity, electromagnetism, strong nuclear force, and the weak nuclear force under a single overarching framework. For the first time, string theory appeared as a promising candidate for the long-sought theory of everything. To understand the basic idea behind string theory, imagine a guitar. Each string on a guitar can vibrate at different frequencies, producing different notes. In the same way, each string in string theory can vibrate at different frequencies, producing different fundamental particles. A string vibrating one way might appear as an electron, while another mode of vibration could make it behave like a photon. Just as a guitarist can create music by manipulating the strings, the universe plays these strings to create particles and forces, forming the intricate symphony of reality. During the mid-1980s, string theorists encountered a new puzzle. Instead of a single unified theory, they had 5 competing versions of string theory, each with different mathematical structures. This was frustrating, as physicists were looking for one cohesive theory to explain everything. But in the 1990s, Edward Witten, a leading theoretical physicist, proposed a new idea. These 5 string theories might actually be different expressions of a single, more fundamental theory. He called this the M theory, which added yet another spatial dimension, bringing the total to 11. Under M theory, strings were not the only fundamental objects. There were also multidimensional branes that could exist in different dimensions. The idea of branes opened up new avenues for understanding our universe, with one of the most intriguing possibilities being that our universe itself could be a 3-dimensional brane floating within a higher dimensional space. This concept suggested that other branes, or parallel universes, might exist alongside ours, leading to groundbreaking ideas about the multiverse. While string theory is mathematically elegant and conceptually beautiful, it's still largely theoretical, as it has yet to make predictions that can be directly tested in experiments. This lack of empirical evidence is one of the major criticisms against string theory. Some physicists argue that a theory that cannot be tested might fall outside the bounds of traditional science. However, supporters of string theory point out that it has provided crucial insights into the nature of black holes, entropy, and even the early moments of the Big Bang. Despite the challenges, string theory remains one of the leading candidates for a theory of everything, guiding physicists toward new mathematical tools and ideas. It has inspired thousands of researchers and has even influenced fields outside of physics, such as pure mathematics. String theory represents humanity's relentless pursuit of understanding the cosmos at the deepest level. It pushes the boundaries of what we know about space, time, and matter, suggesting that the very fabric of reality might be woven from tiny, vibrating strings. Though we may be far from confirming its predictions, string theory serves as a beacon in the quest to uncover the ultimate nature of the universe. Just as the early explorers charted unknown territories, string theorists venture into the abstract landscapes of mathematics and physics, driven by the hope that one day we may have a complete understanding of reality itself. Cosmic microwave background radiation. The discovery of cosmic microwave background, CMB, radiation ranks as one of the most profound breakthroughs in our understanding of the universe. This radiation provides a window back in time, offering scientists a glimpse of the universe as it was nearly 14 billion years ago, shortly after the Big Bang. But the story of how this faint glow of ancient radiation was discovered is one of unexpected finds and scientific curiosity, with roots in a quiet field in New Jersey and theories that emerged decades before. To understand what CMB radiation is, it helps to imagine the universe shortly after the Big Bang. Around 380,000 years post-Big Bang, the universe was a scorching, dense plasma, a thick, foggy soup of protons, electrons, and photons. Light, in the form of photons, was constantly scattering off particles in this plasma, unable to travel freely. Then, as the universe expanded, it cooled down to a temperature low enough for protons and electrons to combine and form neutral hydrogen atoms. This change allowed photons to move freely, filling the universe with light. This moment is known as the epoch of recombination, and the light from this time has been traveling through space ever since. Over billions of years, as the universe expanded further, the wavelengths of these photons stretched out, shifting into the microwave portion of the electromagnetic spectrum, creating what we now detect as the CMB radiation. Long before it was actually discovered, CMB radiation was predicted by theorists in the 1940s. Physicist George Gamow and his colleagues Ralph Alpher and Robert Herman were studying the implications of the Big Bang model and realized that if the universe had indeed begun in a hot, dense state, then there should be residual radiation from that initial phase. They calculated that this leftover radiation would have cooled down by now just a few degrees above absolute zero, and it would permeate all of space. However, this prediction did not immediately lead to experimental searches, and it would take 2 decades before anyone stumbled upon it. In the early 1960s, Arno Penzias and Robert Wilson, 2 radio astronomers at Bell Telephone Laboratories in New Jersey, were experimenting with a large horn antenna designed to detect faint radio signals for satellite communication. But their antenna picked up a mysterious noise they couldn't explain, a faint, persistent hum that seemed to come from every direction in the sky. Penzias and Wilson checked and rechecked their equipment, suspecting technical interference, or perhaps even interference from the nearby city. They cleaned out pigeon droppings from the horn, thinking that might be the cause, yet the noise persisted. It had no identifiable source and didn't vary with the time of day, season, or the direction in which they pointed the antenna. This static remained a puzzle until they heard about the work of Robert Dicke and his team at Princeton University, who were working on the very prediction made by Gamow's team years earlier, the residual radiation from the Big Bang. When Penzias and Wilson reached out to Dicke, he immediately recognized the significance of their findings. His team at Princeton had been searching for evidence of this background, radiation, but they hadn't yet succeeded. Upon hearing about the static Penzias and Wilson had detected, Dicke famously said, "Well, boys, we've been scooped." The signal Penzias and Wilson detected was precisely what Gamow, Alpher, and Herman had predicted, the faint residual radiation from the Big Bang, cooled and stretched into microwaves by the expansion of the universe. This was a monumental discovery, providing the first concrete observational evidence for the Big Bang theory. Following this discovery, the scientific community set out to study the CMB radiation in greater detail. In the 1990s, NASA launched the COBE, Cosmic Background Explorer satellite, which confirmed Penzias and Wilson's findings with much greater accuracy. COBE also found tiny fluctuations in the temperature of the CMB across the sky, variations that correspond to the small density differences in the early universe that would eventually grow to form galaxies, stars, and planets. These fluctuations were like a snapshot of the seeds of structure in the cosmos, allowing scientists to understand how the universe's large-scale structure developed. Later, even more advanced satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite provided even more detailed maps of the CMB. With these maps, scientists could measure the age, composition, and curvature of the universe with unprecedented precision. The CMB radiation became a cosmic blueprint, encoding information about the universe's infancy, composition, and eventual fate. Imagine shouting into a canyon and hearing an echo reverberate back to you. The CMB radiation is like an echo from the early universe, a faint but persistent hum that provides invaluable information about where we came from. Just as the echo reflects the original shout, the CMB radiation reflects the conditions of the early universe, stretched and softened by the vast distances it has traveled. This radiation fills the universe, providing us with a backdrop, a faint afterglow of creation that illuminates the origins of everything we know. The discovery of CMB radiation transformed cosmology. It provided a foundation for the Big Bang theory, allowing scientists to transition from speculative cosmological theories to a concrete model based on empirical evidence. It offered a way to see back to the earliest moments of time, to understand the universe's structure, and even predict its fate. For their groundbreaking work, Penzias and Wilson received the Nobel Prize in Physics in 1978, cementing their accidental discovery as one of the most significant scientific achievements of the 20th century. Today, the study of the CMB continues, with physicists probing it for insights into dark matter, dark energy, and other cosmic mysteries. The CMB radiation, once a mysterious noise on a radio antenna, has become a cornerstone of our understanding of the universe, forever changing the way we view our cosmic origins. Dark matter and dark energy. The discovery of dark matter and dark energy stands among the most intriguing, mysterious chapters in modern physics. These two invisible entities are believed to compose around 95% of the universe, yet they defy direct observation. Their existence was suggested not by sight, but by the strange, unexpected ways they influence the visible cosmos. The story of their discovery is a winding journey of curiosity, mathematical puzzles, and the persistence of scientists who noticed things in the universe weren't quite adding up. The search for dark matter began with a peculiar observation in the 1930s by Swiss astronomer Fritz Zwicky, studying the Coma cluster, a collection of galaxies bound together by gravity. Zwicky noticed something odd. The galaxies were moving far faster than they should have been if their observable mass was all that existed. According to Newton's laws, they should have flown apart at those speeds, yet they remained bound together. Zwicky theorized that there must be some kind of invisible, missing mass holding the galaxies together. He coined the term dunkle materie, or dark matter, to describe this unseen mass, which seemed to provide the gravitational glue binding galaxies in place. While Zwicky's theory was ahead of its time and largely overlooked for years, the idea of missing mass re-emerged in the 1970s, thanks to the pioneering work of American astronomer Vera Rubin. Rubin was studying the rotation curves of individual galaxies, specifically how fast stars orbit around their galactic centers. According to established laws of physics, stars farther from the center of a galaxy should orbit more slowly than those closer in, much like planets around the sun. However, Rubin discovered that stars in galaxies rotated at nearly the same speed, regardless of their distance from the center. This uniform rotation implied that galaxies had far more mass than what was visible in the form of stars, gas, and dust. Like Zwicky, Rubin deduced that galaxies contained an enormous amount of unseen matter that provided the gravitational pull necessary to account for this rotation pattern. Her work offered compelling evidence for dark matter and transformed it from a fringe idea into one of the central questions in cosmology. While dark matter addresses the invisible mass holding galaxies together, dark energy addresses an entirely different mystery, the accelerating expansion of the universe. To understand dark energy, we need to jump forward to the 1990s, when two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, set out to measure the rate of cosmic expansion. At the time, scientists expected the universe's expansion, which began with the Big Bang, to be slowing down due to gravity. After all, if galaxies and clusters are gravitationally attracted to each other, this pull should eventually decelerate the expansion of space itself. To test this theory, Perlmutter, Schmidt, and Rees's teams observed Type Ia supernovae, explosions of dying stars that act like standard candles due to their consistent luminosity, making them ideal for measuring cosmic distances. To their astonishment, the results showed the opposite of what they expected. Rather than slowing down, the universe was expanding faster. It was as if some unseen force was propelling galaxies apart, accelerating the expansion of space itself. This force was named dark energy, an enigmatic pressure countering gravity on a cosmic scale, responsible for pushing galaxies farther and farther away from each other. Imagine watching a play in a theater. The actors, lights, and props on stage are the visible matter we can observe, stars, galaxies, and everything we see in the universe. But for the play to run smoothly, there must be a team of stage managers, lighting coordinators, and directors working behind the scenes, influencing the production without being seen. Dark matter is like the set crew, moving the scenery, setting the stage, and ensuring everything holds together. Dark energy, on the other hand, is like a mysterious director making decisions that alter the play's pacing, creating a dynamic push that influences everything on the stage. In this analogy, dark matter holds galaxies and clusters together, while dark energy accelerates the expansion of the cosmic stage itself, increasing the distance between the galaxies as if constantly adding more space. Today, dark matter and dark energy remain two of the most significant mysteries in science. Dark matter appears to interact primarily through gravity, forming the invisible framework upon which galaxies and clusters are built. Despite decades of experiments, ranging from particle detectors deep underground to high-energy collisions in the Large Hadron Collider, scientists have yet to directly detect a dark matter particle. Current theories suggest it might be composed of exotic particles like WIMPs, weakly interacting massive particles, or axions. But without direct evidence, dark matter's nature remains speculative. Dark energy is even more elusive. Its nature is not fully understood, but one hypothesis links it to the cosmological constant that Albert Einstein once proposed in his equations of general relativity. Ironically, Einstein originally introduced the cosmological constant to keep the universe static, but later discarded it, calling it his biggest blunder when he learned the universe was expanding. In a strange twist, this cosmological constant has returned as a candidate explanation for dark energy. Understanding dark matter and dark energy is crucial because they affect everything from the shape and fate of the universe to the formation of galaxies and the distribution of cosmic structures. Dark matter explains why galaxies cluster in particular patterns, while dark energy hints at the ultimate fate of the universe. Will it continue to expand forever, ripping galaxies apart in a big rip? Or might it reach a balance where expansion halts? These questions depend largely on the behavior of dark energy, which remains one of the most tantalizing unknowns in cosmology. Research on dark matter and dark energy continues with ever-advancing technology. Telescopes like the James Webb Space Telescope and massive surveys like the Dark Energy Survey aim to gather clues about these cosmic mysteries. These tools allow scientists to map out the universe's structure with greater precision, looking for patterns and gravitational effects that could reveal the presence of dark matter or hint at the behavior of dark energy. Ultimately, dark matter and dark energy remind us of how much there is yet to discover. They point to gaps in our knowledge, urging scientists to explore, question, and push the boundaries of what we know. And though they may be invisible to us, their effects shape everything we see in the cosmos, connecting galaxies, influencing cosmic structure, and driving the expansion of the universe itself. The quest to understand them lies at the heart of modern physics, as we continue to unravel the hidden, powerful forces that sculpt the universe. Discovery of the Higgs boson. The discovery of the Higgs boson is one of the most celebrated achievements in modern physics, not just because it solved a long-standing puzzle, but because it represents a triumph of human ingenuity, engineering, and theoretical foresight. The story of the Higgs boson is one of persistence, spanning nearly half a century from its theoretical conception to its experimental confirmation, and it centers on a seemingly simple but incredibly important question: why do particles have mass? In the early 1960s, physicists were developing what we now know as the Standard Model of Particle Physics, a framework that would become a foundation for understanding the fundamental particles and forces. The Standard Model explained a lot, but it had a glaring problem. It could not account for the mass of particles without breaking key symmetries in nature, symmetries that are critical to how particles and forces interact. The equations predicted that particles like W and Z bosons, which mediate the weak force, should be massless, but experiments showed they were massive. Without an explanation for mass, the entire model was incomplete. This was where a group of theorists, including Peter Higgs, stepped in. In 1964, Higgs, along with other scientists like Robert Brute, Francois Englert, Gerald Guralnick, Carl Hagen, and Tom Kibble, proposed a radical solution, a new field, now known as the Higgs field. Higgs theorized that this field permeates the universe like an invisible molasses. As particles move through it, they interact with the field, which slows them down and gives them mass. Some particles, like photons, don't interact with this field and thus remain massless, while others, like the W and Z bosons, interact strongly with it and gain mass. To explain this visually, imagine a crowded room full of people. A person trying to cross the room encounters resistance from the crowd, which slows them down. This is akin to how particles acquire mass as they move through the Higgs field. This field is everywhere, and it interacts with particles based on specific properties causing some to become massive, while others pass through unaffected. If this Higgs field existed, it would imply the existence of a unique particle, the Higgs boson, a quantum ripple in the field. Proving the existence of this particle became one of the great quests in particle physics. However, because of its predicted mass and the energy required to detect it, the Higgs boson was elusive, out of reach for many years. This set the stage for an unprecedented scientific endeavor, the construction of the Large Hadron Collider, LHC. The LHC, located near Geneva, Switzerland, is a massive underground particle accelerator operated by CERN, the European Organization for Nuclear Research. The LHC was designed to smash protons together at speeds near the speed of light, creating conditions so extreme that they could mimic the universe's state just after the Big Bang. In these collisions, particles break apart and interact, releasing massive amounts of energy. This process has the potential to produce heavy particles like the Higgs boson, if it exists. After years of planning and construction, the LHC began operations in 2008. Thousands of scientists and engineers from around the world collaborated on experiments specifically designed to search for the Higgs. These experiments, particularly the ATLAS and CMS experiments, were designed to detect and analyze the fleeting signs of particles produced in these high-energy collisions. Detecting the Higgs boson was no easy task. Scientists were looking for extremely subtle signs among a flood of other particle events. The Higgs boson itself decays almost immediately after it is produced, leaving behind signatures that are notoriously difficult to isolate from background noise. The data had to be filtered, analyzed, and reanalyzed to confirm any possible evidence of the Higgs. Finally, on July 4, 2012, scientists at CERN announced they had observed a particle consistent with the Higgs boson. Both the ATLAS and CMS experiments independently confirmed this result with a high degree of confidence. The discovery was hailed as a monumental breakthrough, providing the missing piece of the Standard Model and confirming the existence of the Higgs field, which imparts mass to particles. The announcement made headlines worldwide, and Peter Higgs himself, who was present at CERN that day, was visibly moved, overwhelmed by the realization of an idea he had proposed nearly 50 years earlier. The Higgs boson is sometimes called the God particle because it completes our understanding of the Standard Model, but it's more than just a theoretical milestone. The Higgs field is essential for explaining why the universe is structured as it is, with galaxies, stars, planets, and life as we know it. Without the mass generated by the Higgs field, particles wouldn't clump together to form atoms, let alone complex structures. The discovery of the Higgs boson has also opened new avenues in particle physics, providing clues that may one day help us understand mysteries like dark matter and gravity. To understand the Higgs field, imagine the universe as a vast canvas and particles as paintbrushes. The canvas has a slight resistance that affects how the paint flows. Depending on the thickness of the brush, some strokes glide easily, while others struggle against the resistance. The Higgs field is like that resistance on the canvas, determining how heavy each stroke appears. For particles in the universe, this field gives them mass, affecting how they move, interact, and combine to form everything we observe. The discovery of the Higgs boson was a crowning achievement, but it is also just the beginning. The properties of the Higgs boson itself may hold secrets to physics beyond the Standard Model, such as supersymmetry or extra dimensions. Today, physicists are probing the Higgs boson with greater precision, hoping to uncover deviations or peculiarities that could lead to new discoveries. In essence, the Higgs boson is a window into the deeper structure of reality. It reveals how particles acquire mass, why they come together to form matter, and what underpins the very fabric of the universe. The journey of its discovery is a testament to human curiosity, collaboration, and perseverance, and it serves as a reminder that, in physics, every answer leads to new, intriguing questions. Gravitational waves. Detection. Gravitational waves, ripples in the fabric of space-time itself, are one of the most fascinating and profound predictions of Einstein's theory of general relativity. For over a century, these waves were theorized but remained elusive, seemingly beyond our reach. Yet, in 2015, after decades of scientific pursuit, These invisible waves were detected for the first time, confirming one of the most profound predictions in physics. This discovery opened a new era in astrophysics, allowing us to listen to the universe in a completely new way. The concept of gravitational waves first arose from Albert Einstein's general theory of relativity, published in 1915. The theory revolutionized our understanding of gravity, not as a force between masses, but as the warping or curvature of space-time caused by the presence of mass and energy. Imagine space-time as a giant trampoline. When you place a heavy ball in the center, it causes the fabric to stretch and curve. Smaller objects, like marbles, roll toward the ball, following the curvature of the fabric. In the same way, planets and stars follow curved paths in the fabric of space-time. Einstein's equations predicted that massive objects, when they move, cause ripples in this fabric, gravitational waves. These waves are created when massive objects like black holes or neutron stars accelerate, particularly in events like mergers, where two massive objects collide and spiral into each other. However, Einstein himself wasn't certain that gravitational waves could ever be detected. The waves, if they existed, would be incredibly faint by the time they reached Earth, making their detection extraordinarily difficult. The idea that gravitational waves could be detected was captivating, but how could such faint disturbances in space-time be measured? The waves would stretch and compress space itself, but the effect on objects would be minuscule, far too small to be detected by ordinary instruments. Even if two black holes collided, the stretching and squeezing caused by the waves would alter distances by less than 1,000th of the size of a proton. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory, an ambitious project born out of decades of work by physicists like Rainer Weiss, Kip Thorne, and Barry Barish. The LIGO experiment, which began in the 1990s, was designed to detect these subtle distortions in space-time by measuring the minute changes in the distance between two mirrors placed miles apart. LIGO works by using an interferometer, a device that measures changes in the distance between two mirrors along two perpendicular arms. A laser beam is split in two, with one part traveling down each arm. After reflecting off the mirrors, the beams are recombined. If a gravitational wave passes through the Earth, it causes a tiny distortion in the length of one arm of the interferometer, altering the pattern in which the laser beams recombine. This shift, though infinitesimally small, can be detected by extremely sensitive equipment. On September 14, 2015, LIGO achieved the unthinkable. At 9 hours 50 minutes and 45 seconds UTC, both LIGO detectors, one located in Hanford, Washington, and the other in Livingston, Louisiana, simultaneously recorded a signal that could only be explained by the passage of gravitational waves. The waves had been produced by the collision and merger of two black holes, each about 30 times the mass of the Sun, located roughly 1.3 billion light-years away. The signal, which lasted less than a second, showed a distinctive chirp, a rapid increase in frequency and amplitude as the black holes spiraled toward each other and merged. The event was so powerful that it released more energy in a fraction of a second than the combined energy output of all the stars in the observable universe. The energy released was in the form of gravitational waves that rippled across the universe and were detected by LIGO. This first detection of gravitational waves was a monumental moment in physics and astronomy. The confirmation of the waves not only verified Einstein's century-old prediction, but also opened a new window into the universe. The discovery was made by a team of scientists working together across the world, and it was an extraordinary validation of decades of hard work, ingenuity, and belief in a theory that had often been considered too speculative to test. The detection of gravitational waves has profound implications for our understanding of the universe. It allows us to hear the violent energetic events that occur far beyond the reach of traditional telescopes. Gravitational waves carry information about the most extreme environments in the universe, places where space-time is warped and where gravity is incredibly intense, such as black hole mergers, neutron-star collisions, and supernovae. Before this breakthrough, astronomers were limited to observing the universe through electromagnetic radiation, light, radio waves, X-rays, and so on. But gravitational waves are a new kind of signal, one that reveals aspects of the universe that were previously hidden. These waves provide insights into the nature of black holes, the formation of galaxies, and the very fabric of space-time itself. For instance, since the detection of the first gravitational wave signal, LIGO has recorded multiple other events, such as neutron-star mergers, which are especially important for understanding phenomena like gamma-ray bursts and the production of heavy elements like gold and platinum. Gravitational wave astronomy has become a vibrant field of research, and its future looks even brighter as more detectors come online around the world, such as the Virgo detector in Europe and future planned detectors like LISA, Laser Interferometer Space Antenna, which will operate in space. The discovery of gravitational waves has not only confirmed Einstein's predictions, but also challenged our understanding of the universe in ways we're still coming to terms with. It opens the door to new theories, new questions, and new kinds of observations. For example, one of the most exciting prospects is the potential to directly study the interiors of black holes, regions where no light can escape. Gravitational waves could allow us to peer into the heart of these cosmic giants, offering a new way to study one of the most enigmatic objects in the universe. Additionally, gravitational wave detection provides a powerful tool for testing the limits of Einstein's theory of general relativity. While the theory has passed every test thrown at it so far, the detection of gravitational waves gives physicists the chance to test its predictions in extreme environments where the usual laws of physics break down. Imagine you're standing by a calm lake, watching ripples form when a stone is thrown into the water. The ripples travel outward, carrying information about the disturbance in the water. In much the same way, gravitational waves travel through the fabric of space-time, carrying information about the most violent and energetic events in the universe, just as the ripples on the water tell you something about the object that caused them. Gravitational waves tell us about the cosmic events, black hole mergers, neutron-star collisions, that created them. Before 2015, gravitational waves were mere speculation. Now, they are a tool for exploring the universe in ways that were previously unimaginable. The discovery of gravitational waves marked the dawn of a new age of cosmic exploration, allowing us to listen to the universe in a way we never could before, revealing a deeper, more mysterious cosmos than we ever imagined. Exoplanet detection and implications for life. For centuries, humanity has looked up at the stars, pondering the existence of life beyond Earth. The idea of other worlds, perhaps similar to our own, teeming with life, has fueled science fiction stories and philosophical debates. Yet, for most of history, this was purely speculative. That is, until science began to answer the question with a resounding yes. The discovery of exoplanets, planets orbiting stars beyond our own solar system, has not only confirmed that the universe is filled with other worlds, but has also opened up profound possibilities for the existence of life elsewhere. But how did we find these distant planets, and what are the implications for life beyond Earth? The story of exoplanet discovery began relatively recently, with the first confirmed exoplanet found in 1992. However, the journey to this discovery was paved with years of scientific progress, starting from a theoretical framework and evolving with advances in technology. In the 1980s, astronomers began developing methods to detect planets around other stars. But detecting exoplanets is a tricky business. Stars are so bright and distant that any planets around them are often completely overshadowed. Astronomer Alexander Woljan and his colleague Piotr Mazur made the groundbreaking discovery of the first confirmed exoplanet, not around a regular star, but around a pulsar, a highly magnetized, rapidly rotating neutron star. The pulsar, named PSRB 1257+12, emitted regular pulses of radio waves, and its regularity allowed Woljan and Mazur to detect small gravitational wobbles caused by the presence of orbiting planets. This was a small but significant step. The planets were extremely unusual, small and rocky, with no potential for life, but they demonstrated that exoplanets could exist outside our solar system. Although the pulsar planets were a milestone, the real revolution in exoplanet detection came with the launch of the Kepler Space Telescope in 2009. Kepler was designed specifically to hunt for Earth-like planets in the habitable zone, the region around a star where conditions might be right for liquid water and potentially life to exist. Kepler's primary method of detecting exoplanets was the transit method. The idea is simple but ingenious. When a planet passes in front of its star, as seen from Earth, it blocks a tiny fraction of the star's light, causing a slight dimming. By measuring these dimming events precisely, astronomers can determine the size of the planet, its orbit, and even its composition. Because Kepler stared at a patch of sky for over 9 years, it observed thousands of stars, carefully measuring the subtle dimming effects caused by orbiting planets. In 2012, Kepler made an incredible announcement. It had identified over 2,300 potential exoplanets. Many of these were Earth-sized or smaller, and some were in the habitable zone of their stars. This was a game-changer. For the first time, we were not only finding exoplanets, but identifying potentially habitable worlds, planets that might host life in ways we had only previously dreamed of. The discovery of Kepler 22b, an exoplanet, in the habitable zone of its star, was one of the most exciting early finds. It's about 600 light-years away from Earth, but its discovery sent shockwaves through the scientific community, suggesting that planets in the habitable zone could be relatively common in our galaxy. As technology improved, so did our ability to detect a wider range of planets. By 2015, astronomers had discovered a staggering 1,000 confirmed exoplanets, and the discoveries have continued to accumulate at an even faster pace. Many of these planets are in unexpected places, challenging previous assumptions. For example, some exoplanets are much larger than Jupiter and orbit extremely close to their stars, while others are super-Earths, planets with masses larger than Earth, but smaller than Uranus or Neptune. Beyond the transit method, scientists have developed other techniques for finding exoplanets. The radial velocity method, also known as the Doppler method, detects the gravitational tug that a planet exerts on its parent star. As a planet orbits a star, it causes the star to wobble slightly. This wobble shifts the star's light toward the red or blue end of the spectrum, depending on whether the star is moving toward or away from Earth. By measuring these shifts, astronomers can detect the presence of planets, even without seeing them directly. Another method is direct imaging, which involves blocking out the light of a star to reveal the planets surrounding it. This technique is more challenging, but has provided fascinating results, especially in the case of young, hot exoplanets that shine brightly in infrared light. The discovery of exoplanets raises one of the most profound questions of our time. Is there life out there? Given the vast number of planets in the universe, many of which share similarities with Earth, the possibility that life could exist elsewhere seems increasingly likely. In 2015, astronomers discovered Proxima b, a planet located in the habitable zone of the star Proxima Centauri, the closest star to our Sun. This discovery sparked widespread excitement, as it's possible that Proxima b has liquid water on its surface, one of the key ingredients for life. While we can't say for sure if life exists on Proxima b, its discovery suggests that Earth-like conditions are not as rare as once thought. One of the most exciting aspects of exoplanet research is that it allows us to study planets in ways we couldn't before. For example, scientists are using spectroscopy to study the atmospheres of distant exoplanets. By analyzing the light that passes through or is reflected by an exoplanet's atmosphere, scientists can detect the presence of key molecules like water vapor, oxygen, or methane, molecules that could be associated with life. This technique, known as atmospheric characterization, is giving us our first glimpses of alien worlds and may one day help us identify planets that have the right conditions for life. The hunt for Earth-like planets, or Earth 2.0, continues to be one of the most exciting endeavors in modern science. While we have yet to find a perfect twin of Earth, the discovery of thousands of exoplanets, some of which lie in their star's habitable zone, gives us hope. In the coming decades, as telescopes like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope come online, we may be able to directly analyze the atmospheres of exoplanets in unprecedented detail. What does all of this mean for us? The discovery of exoplanets has shifted our perspective on the universe. It suggests that we are not alone in a barren cosmos, but part of a vast star-filled expanse teeming with possibilities. Whether we find life on an exoplanet or not, the search helps us understand our own planet, the conditions that make life possible, and our place in the universe. By exploring these distant worlds, we not only seek the potential for life beyond Earth, but also ask fundamental questions about existence itself. What makes a planet habitable? What role does life play in the grand cosmos? The discovery of exoplanets is a profound reminder that we are not isolated in the universe. We are part of an incredible cosmic experiment, one that is just beginning to reveal its secrets. Quantum computing and information theory. In the 1980s, physicist Richard Feynman famously said, "If you're not confused by quantum mechanics, you don't understand it." His statement encapsulates the oddness of the quantum world, where particles can exist in multiple states simultaneously, and where information behaves in ways that defy classical intuition. But this strange realm also holds the key to a breakthrough in computation and information theory that could revolutionize our world. This breakthrough is quantum computing, a concept that, at its heart, harnesses the unique properties of quantum mechanics to process information in entirely new ways. The idea of quantum computing emerged from the realization that classical computers, those powered by bits, might not be able to solve certain problems efficiently. Bits, the basic unit of classical information, can exist in one of two states, 0 or 1. While this binary system works for many tasks, it's not suitable for problems that require immense computational power, such as simulating the behavior of molecules at the quantum level or factoring large numbers for cryptography. In 1981, Feynman proposed a novel idea. Instead of relying on classical bits, why not exploit the power of quantum mechanics itself? Quantum mechanics is the branch of physics that deals with particles at the smallest scales, where phenomena like superposition, being in multiple states at once, and entanglement, instantaneous connections between particles, no matter the distance, occur. Feynman suggested that we could design a machine that harnesses these properties to simulate quantum systems far more efficiently than classical computers could. The seeds for quantum computing were planted in this moment. Feynman wasn't the only one thinking along these lines. In 1985, physicist David Deutsch of Oxford University took the next crucial step, creating a mathematical model for a quantum computer, which became known as the Deutsch model. His work laid the groundwork for understanding how a quantum computer could theoretically function. To understand how quantum computers work, we need to dive into two fundamental quantum phenomena: superposition and entanglement. Superposition. In the quantum world, particles like electrons don't just exist in one state at a time. They can exist in multiple states simultaneously. Imagine flipping a coin. It can either land heads or tails. But in the quantum world, the coin can be in a superposition of heads and tails at the same time until you observe it. Quantum computers exploit this ability, allowing a quantum bit or qubit to be both 0 and 1 simultaneously. This opens the door to processing vast amounts of information at once, vastly increasing the computational power compared to classical bits. Entanglement. When two quantum particles become entangled, their states are linked, no matter how far apart they are. If you measure one particle, you instantly know the state of the other, even if it's light years away. In quantum computing, entanglement allows qubits to work together in ways classical bits cannot, enabling quantum computers to solve complex problems exponentially faster than traditional computers. With the basic principles of quantum computing in place, the next step was to develop algorithms that could harness the power of qubits. In 1994, physicist Peter Shor made a groundbreaking contribution. He developed an algorithm that could factor large numbers exponentially faster than any known classical algorithm. This was a game changer because factoring large numbers is a core task in cryptography, specifically in RSA encryption, which is widely used to secure online communications. If a quantum computer could break RSA encryption, it would represent a monumental shift in the field of cybersecurity. Shortly after, In 1996, Love Grover developed an algorithm that could search unsorted databases faster than classical computers, a task that traditionally requires examining each entry one by one. Grover's algorithm demonstrated that quantum computers could provide speed-ups for a wide variety of tasks beyond number factoring, from optimization problems to machine learning. These developments sparked interest across both academia and industry, and the race to build a functioning quantum computer began in earnest. Building a quantum computer, however, is no simple feat. The fragile nature of quantum states, affected by factors like temperature, noise, and electromagnetic radiation, makes it incredibly challenging to create a stable qubit. Several approaches emerged to overcome these challenges, including trapped ions, superconducting circuits, and topological qubits. Trapped ions. In this approach, ions, charged atoms, are trapped using electromagnetic fields and manipulated with lasers. Each ion acts as a qubit, and their interactions are controlled by the laser pulses. This method has shown remarkable promise in lab experiments and has led to the development of small-scale quantum computers. Superconducting circuits. This approach involves using superconducting materials that can conduct electricity with zero resistance when cooled to extremely low temperatures. These circuits behave like tiny artificial atoms and can be used as qubits. Companies like IBM and Google have made significant progress with superconducting qubits, with Google's Sycamore processor famously achieving quantum supremacy in 2019 by solving a problem that would have taken a classical supercomputer thousands of years to complete. Topological qubits. A more speculative approach. Topological qubits are designed to be more resistant to error by encoding information in the topology of the quantum system. While this approach remains largely theoretical, it promises to solve one of the biggest challenges in quantum computing: error correction. While a fully functional large-scale quantum computer remains elusive, significant strides have been made in building quantum processors capable of solving specific problems. In addition to the breakthroughs in hardware, advances in quantum error correction, quantum communication, and quantum cryptography are being made at a rapid pace. Quantum computing's potential extends beyond just speed. It could unlock new solutions to complex problems in fields ranging from material science, designing new drugs or better solar panels, to artificial intelligence, creating more efficient machine learning models. For instance, quantum computers could simulate chemical reactions at the atomic level, something classical computers struggle to do. This could lead to breakthroughs in drug development, energy storage, and new materials that are currently beyond our reach. Today, companies like IBM, Google, and Microsoft are leading the charge to make quantum computing a practical reality. Startups like Rigetti Computing and IonQ are also pushing the envelope. Governments around the world are investing heavily in quantum research as the technology promises to reshape industries from finance to healthcare. But quantum computing also presents new challenges and questions. If quantum computers can break traditional encryption schemes, how can we protect our data? This is where quantum cryptography comes in, offering new ways to secure information through the principles of quantum mechanics itself. Ultimately, the discovery of quantum computing is still in its infancy, but its potential to change the world is vast. From solving problems too complex for even the fastest classical supercomputers to unlocking new technologies, quantum computing may be the next frontier in our understanding of the universe and in how we manipulate information to change the world. The theory of everything. Imagine trying to put together a jigsaw puzzle. Each piece represents a different aspect of the universe, the forces of nature, the behavior of matter, the structure of space and time. Now imagine that the pieces of the puzzle fit together perfectly, revealing a single unified picture that explains everything, from the smallest particles of matter to the largest galaxies. This is the ultimate dream of physics, a theory of everything, TOE, a single framework that unifies all the forces of nature into one coherent explanation. For centuries, scientists have been working toward this elusive goal, and while it remains one of the greatest challenges in science, progress has been made. Let's take a journey through the history of the theory of everything, examining the discoveries that have brought us closer to this monumental understanding. In the early 20th century, physics was already fragmented into two main pillars. The first was classical mechanics, which explained the motion of objects in everyday life. The second was electromagnetism, the theory governing electric and magnetic forces, brilliantly formulated by James Clerk Maxwell in the 19th century. Maxwell's equations showed that light itself was an electromagnetic wave, linking electricity and magnetism in a beautiful, unified theory. But then came a radical shift with the advent of quantum mechanics and general relativity, two ideas that redefined our understanding of the universe in very different ways. Quantum mechanics, developed in the early 20th century by pioneers like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, revealed that at the microscopic level, particles don't behave like solid objects. They act more like waves with probabilities and uncertainties. The concept of wave-particle duality and the uncertainty principle shattered the classical understanding of reality. General relativity, developed by Albert Einstein in 1915, gave us a new understanding of gravity. Einstein proposed that gravity isn't a force in the traditional sense, but rather a result of the warping of space-time by mass and energy. This was a far cry from Newton's classical theory of gravity, but it provided a more accurate description of the universe, especially in extreme conditions like black holes and the cosmos itself. These two theories, quantum mechanics and general relativity, were each incredibly successful in their respective domains. Quantum mechanics governed the microscopic world of atoms and particles, while general relativity described the behavior of massive objects like planets, stars, and galaxies. However, they didn't mix well. The two frameworks were fundamentally incompatible, and they couldn't explain everything. The first major step toward a theory of everything came in the mid-20th century with the development of quantum field theory. QFT. QFT combines the principles of quantum mechanics with special relativity and is the framework in which we understand the behavior of particles and forces. But what really brought things together was the discovery that three of the four fundamental forces of nature, electromagnetic force, weak nuclear force, and strong nuclear force, could be unified into a single framework. The standard model of particle physics is the culmination of this effort. It describes the particles that make up matter and the forces that govern them. The standard model successfully unified the electromagnetic and weak nuclear forces into the electroweak theory in the 1970s, earning physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg the Nobel Prize in Physics in 1979. In the 1980s, the discovery of the Higgs boson completed the model by explaining how particles acquire mass. The standard model, however, leaves a significant gap. It doesn't include gravity. Gravity is still described by Einstein's general relativity, and no one has yet figured out how to incorporate it into the framework of quantum mechanics. This is where the theory of everything comes into play. By the 1980s, the search for a theory of everything turned to the idea that everything in the universe could be explained by tiny vibrating strings. String theory suggests that the fundamental building blocks of the universe are not particles, but tiny one-dimensional strings that vibrate at different frequencies. These strings could explain the various particles and forces of nature as different vibrational modes of the same underlying entity. String theory offers a possible unification of quantum mechanics and general relativity because it provides a framework in which gravity can be naturally included alongside the other forces. In string theory, the force of gravity is mediated by a hypothetical particle called the graviton, a quantum particle that would be responsible for transmitting the gravitational force. By integrating gravity into the quantum framework, string theory could be the key to a theory of everything. However, string theory is still highly theoretical. It requires the existence of additional spatial dimensions beyond the familiar three: height, width, depth. In fact, string theory suggests there could be as many as 10 or 11 dimensions in total. These extra dimensions are not immediately observable because they are thought to be curled up at scales so small they cannot be detected with current technology. Despite its elegance and potential, string theory has yet to make testable predictions that could confirm its validity. It's also a highly mathematical and abstract framework, making it difficult to visualize or test in experiments. This has led some to criticize string theory for being too speculative, while others remain hopeful that it will eventually lead to a unified theory. While string theory remains the leading candidate for a theory of everything, it's not the only idea on the table. Another approach called loop quantum gravity attempts to combine quantum mechanics and general relativity without relying on the idea of strings. Instead, loop quantum gravity suggests that space-time itself is quantized, composed of discrete chunks or loops at the smallest scale. While this approach is still in its infancy compared to string theory, it has the advantage of being more directly related to Einstein's original equations of general relativity, without requiring extra dimensions or the highly abstract concept of strings. It is one of many theories being explored in the search for a complete theory of quantum gravity. So how close are we to a theory of everything? Despite the tremendous progress made over the past century, the final unification of all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, remains an open question. The search for a TOE is ongoing, with new developments in quantum mechanics, string theory, and quantum gravity emerging all the time. You see, one of the biggest challenges is that the scales at which quantum mechanics and general relativity operate are vastly different. Quantum mechanics governs the tiny scales of atoms and particles, while general relativity governs the vast expanses of the universe. Bringing these two together requires new mathematical frameworks and new ways of thinking about the fabric of reality itself. The journey towards a theory of everything is as much about the questions we ask as the answers we find. Whether string theory, loop quantum gravity, or some other theory ultimately holds the key, the quest for a unified theory is a testament to the curiosity and determination of humankind. It's a reminder that despite our current understanding of the universe, we are still only scratching the surface of its deepest secrets. In the end, the theory of everything is not just about understanding the universe, it's about comprehending our place within it. And that's a pursuit that will continue to inspire generations of physicists and dreamers alike. Extra dimensions and Brane theory. Imagine you're living in a two-dimensional world, a flat plane like a piece of paper. You move in two directions, forward and backward, left and right. Now, imagine that you're suddenly told there are extra directions you can't see or experience, directions that go above and below the plane of your existence. These hidden dimensions might sound strange, but this is the idea behind extra dimensions in physics, a concept that challenges everything we know about space and reality itself. The notion that there might be more dimensions than the familiar three, height, width, and depth, has been a provocative idea in theoretical physics for over a century, but it wasn't until the late 20th century, with the advent of string theory and the exploration of Brane theory, that the idea of extra dimensions started to take shape in a more formal and scientifically grounded way. The idea of extra dimensions isn't as new as it might seem. The first serious attempt to unify gravity with electromagnetism through extra dimensions came in the 1920s with the work of Theodor Kaluza and Oskar Klein Kaluza, a German physicist, proposed that the force of gravity could be described by a fifth dimension in addition to the familiar four of space and time. Klein, building on Kaluza's work, suggested that this extra dimension could be curled up at a very small scale, which is why we can't observe it. This idea, known as Kaluza-Klein theory, was a bold and imaginative attempt to unify the fundamental forces of nature, but it remained an abstract concept with no experimental support at the time. However, as the century progressed and quantum mechanics and relativity grew more established, the idea of extra dimensions would come to play a pivotal role in the development of string theory. In the 1980s, string theory emerged as a powerful framework that sought to unify the forces of nature. String theory proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny vibrating strings. These strings can vibrate in different modes, with each mode corresponding to a different particle. For string theory to work mathematically, It requires the existence of more than just the familiar 3 spatial dimensions and 1 time dimension. In fact, string theory suggests that there are 10 dimensions in total, 9 spatial dimensions and 1 time dimension. These extra dimensions, however, are not immediately observable because they are thought to be compactified, curled up so small that they exist on scales far beyond the reach of current experiments. This concept of compactification, where extra dimensions are hidden from our direct observation, was a key element in making string theory a mathematically viable framework. As string theory developed, it wasn't just the idea of extra dimensions that caught physicists' attention. It was also the idea of branes, short for membranes. Branes are higher dimensional objects that can exist in these extra dimensions. While a point-like particle is zero-dimensional and a string is one-dimensional, branes can have multiple dimensions. For instance, a 2-brane would be a 2-dimensional object like a sheet. A 3-brane would be a 3-dimensional object like a cube, and so on. The key insight from brane theory developed in the 1990s as part of M-theory, a broader framework that includes string theory, is that our universe may itself be a 3-brane embedded in a higher dimensional space. In this scenario, our familiar 3D world is confined to a brane, while extra dimensions and other branes might exist in a higher dimensional space. One of the striking implications of brane theory is that gravity might not be confined to our 3-brane. According to string theory and brane models, gravity could leak into higher dimensions, which could explain why gravity is so much weaker than the other fundamental forces. If gravity spreads out into the extra dimensions, it would appear much weaker in our 3-dimensional world compared to the forces of electromagnetism, the strong force, and the weak force. What does all this mean for our understanding of the universe? Extra dimensions and brane theory offer radical new ways of thinking about space, time, and the fundamental forces of nature. Here are a few key implications of these ideas. 1. Unification of forces. Extra dimensions provide a framework where the forces of nature could be unified. In string theory, the existence of extra dimensions helps explain the behavior of particles and forces, including gravity, in a single, unified framework. This brings us closer to the dream of a theory of everything, a single theory that can explain all the forces of nature from the smallest particles to the largest cosmic structures. 2. Hidden realities. If there are extra dimensions beyond the ones we experience, this suggests the existence of hidden realms or realities that we cannot directly perceive. In the context of brane theory, our entire universe could be a 3-dimensional brane, floating within a higher dimensional space. This raises the possibility of parallel universes, other branes that exist in the same higher dimensional space but don't interact with ours in any observable way. 3. Dark matter and dark energy. Some physicists have speculated that extra dimensions and branes could help explain some of the greatest mysteries of modern physics, such as dark matter and dark energy. These invisible phenomena make up most of the mass and energy in the universe, yet we cannot detect them directly. If gravity spreads into higher dimensions, it could be interacting with hidden matter or energy in ways that we don't yet understand. 4. Cosmic evolution. Brane theory also has implications for the origins of the universe. One popular idea suggests that the Big Bang may have been the result of a collision between 2 branes. In this scenario, the universe we see today could be just one outcome of a much larger, more complex process involving higher dimensional objects. While extra dimensions and brane theory provide an elegant and mathematically rich framework, they are still speculative. We have yet to observe higher dimensional phenomena or directly detect branes. The idea of extra dimensions is tantalizing, but experimental evidence remains elusive. Some theories suggest that we may one day detect signs of extra dimensions through high-energy particle collisions or the study of cosmological phenomena, but for now, we are still in the realm of theoretical physics. As technology and experimental techniques improve, we may one day be able to test these ideas and uncover the hidden dimensions of our universe. Until then, the concept of extra dimensions and branes remains one of the most fascinating frontiers of theoretical physics. opening up new possibilities for understanding the fabric of reality itself. In the end, extra dimensions and Brane theory offer a glimpse into a universe far more complex and mysterious than we could have ever imagined. They challenge our perceptions of space, time, and the very nature of existence, pushing the boundaries of our knowledge and inviting us to think beyond the limits of our three-dimensional experience. The Multiverse Theory. Picture a grand cosmic library, an infinite structure that houses every possible book you could imagine. Each book represents a different universe, each with its own unique set of rules, histories, and events. Some are similar to ours, with only subtle differences, while others are vastly different, governed by entirely different laws of physics. This library of books is the multiverse, a vast, ever-expanding collection of parallel universes that coexist alongside our own. The idea of the multiverse is one of the most mind-bending and controversial concepts in modern physics. It suggests that the universe we inhabit is not the only one that exists, but just one of many possible realities. But how did this idea come about? Let's trace its origins and explore how it has evolved over time. The first inklings of the multiverse can be traced back to the early 20th century, when the foundations of modern physics were being laid. The discovery of quantum mechanics and the development of cosmology introduced new ways of thinking about reality. In quantum mechanics, particles didn't follow predictable paths. Instead, their behavior seemed governed by probabilities. This led to the famous Copenhagen interpretation, which suggested that particles could exist in multiple states at once, until observed. But the real spark for the multiverse theory came from a seemingly unrelated development: the many-worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957. Everett's groundbreaking idea was that instead of the universe collapsing into one definitive state when we observe it, every possible outcome of a quantum event actually happens, just in separate, non-interacting branches of the universe. Imagine tossing a coin. Instead of the coin landing as heads or tails, both outcomes occur, but in different parallel universes. Each universe is its own branch, created by the different possible results of quantum events. This idea was revolutionary. It suggested that the universe we experience is just one of the infinite number of possible realities, each one existing in parallel. The many worlds interpretation provided a possible framework for understanding how the multiverse might exist, though it was at the time more of a mathematical curiosity than a testable theory. While Everett's many worlds interpretation planted the seeds of the multiverse theory, it was the work of cosmologists in the late 20th century that brought the idea closer to mainstream science. The advent of the inflationary model of the universe developed by Alan Guth in the early 1980s set the stage for the multiverse to emerge as a scientific theory. In simple terms, cosmic inflation is the idea that in the first moments after the Big Bang, the universe expanded exponentially at an incredibly rapid rate. This expansion stretched the fabric of space-time so quickly that small quantum fluctuations in the early universe could grow into the galaxies and structures we observe today. These fluctuations became the seeds of cosmic diversity. But what inflation also suggested was something far stranger. Regions of space could inflate at different rates, leading to different pockets of space-time, each evolving into its own universe with its own set of physical laws. This was the birth of the idea of eternal inflation, the notion that inflationary expansion didn't stop with our universe but continues indefinitely, creating an endless number of pocket universes or bubbles, each with its own distinct properties. This is one version of the multiverse theory, the bubble multiverse. In this scenario, the Big Bang is not a one-time event, but part of an ongoing process of universe creation, with each bubble universe having its own Big Bang and its own physical constants, such as gravity, the speed of light, and even the laws of physics. As the multiverse idea gained traction in cosmology, it also found a natural home in the world of string theory, a framework that attempts to unify all the forces of nature. String theory proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings exist in higher dimensions, beyond the familiar three dimensions of space and one of time. String theory suggests that there could be a vast landscape of possible solutions to the equations of the theory, each corresponding to a different set of physical laws. This idea is known as the string landscape. In this context, the multiverse is seen as a natural consequence of string theory's extra dimensions. There could be a vast number of different ways that the extra dimensions are compactified, curled up on tiny scales that we cannot observe. Each compactification could result in a different set of physical laws, creating a separate universe. The landscape of possible universes is so vast that, according to string theory, it's highly likely that other universes exist, each one with its own unique properties. In fact, some proponents of string theory argue that the multiverse is an unavoidable result of the theory itself. The constant creation of universes with different properties would explain the fine-tuning of the constants of nature, why the conditions of our universe seem so perfectly suited for life. If there are enough universes, then, by pure chance, some would have the right conditions for stars, planets, and even life to emerge. If the multiverse theory is correct, it raises profound questions about the nature of reality. Here are a few of the key implications. 1. The fine-tuning problem. One of the central mysteries of cosmology is why the constants of nature, like the strength of gravity or the mass of the electron, are so perfectly tuned to allow life to exist. The multiverse offers an explanation. In a universe with an infinite number of possibilities, some universes will have the right conditions for life by chance. 2. The nature of probability. If every possible outcome of every quantum event occurs in a separate universe, it challenges our understanding of probability and fate. The idea that everything that could happen does happen somewhere in the multiverse could have profound philosophical implications. 3. The limits of observation. One of the main challenges of the multiverse theory is that, in most versions, the other universes are forever beyond our reach. Since they don't interact with ours, we have no way of observing them directly. This raises the question of whether the multiverse is truly scientific or if it is simply a philosophical idea. Despite the tantalizing implications of the multiverse, it remains a controversial and speculative theory. There is, as yet, no direct evidence for the existence of other universes, and testing the idea is a monumental challenge. However, the concept of the multiverse continues to inspire new research in cosmology, quantum mechanics, and string theory. If we ever develop the tools to test the multiverse hypothesis, it would mark a new era in our understanding of the cosmos, one in which the universe we call home is no longer the only reality. Whether or not the multiverse exists, the idea forces us to confront some of the most profound questions about existence, reality, and the very nature of the cosmos itself. For now, the multiverse remains a tantalizing possibility, an idea that challenges the very fabric of reality and offers a glimpse into the unimaginable vastness of the cosmos. The information paradox in black holes. Imagine you're standing before a massive black hole, the most mysterious and powerful object in the universe. As you approach, you notice an oddity. Objects, light, even information about what falls into it, seem to disappear entirely, lost forever. But is that truly the case? Does information vanish, or does it somehow persist in ways we can't yet comprehend? This is the essence of the information paradox in black holes, one of the deepest puzzles in modern physics. To understand this enigma, we need to trace its origins, the discoveries that led to it, and the ongoing efforts to resolve it. The story of the information paradox begins with the legendary physicist Stephen Hawking in the 1970s. Until that point, black holes were mostly thought of as objects with such intense gravity that nothing, not even light, could escape their grasp. This point of no return is known as the event horizon, the boundary beyond which nothing can escape, not even information. However, Hawking's work would challenge this classical view. In 1974, Hawking made a stunning discovery. Black holes emit radiation. This radiation, now known as Hawking radiation, arises from quantum effects near the event horizon. It's as if the black hole is slowly leaking energy, and over time it can even cause the black hole to shrink and eventually evaporate completely. This revelation was groundbreaking because it suggested that black holes weren't permanent. They could eventually vanish. But it was this discovery that also laid the foundation for the information paradox. According to the laws of quantum mechanics, information about the state of a system, whether it's the position of particles or the properties of energy, cannot be completely lost. Even if a black hole evaporates through Hawking radiation, the information contained within it should, in theory, be preserved. After all, quantum mechanics holds that information is always conserved, a principle that underpins much of our understanding of the universe. But here's the rub. If a black hole evaporates and disappears, taking all its mass and energy with it, where does the information go? The radiation emitted by the black hole doesn't seem to carry any information about the objects that fell into it. In fact, the radiation looks completely random. This creates a paradox. If the black hole evaporates and takes all the information with it, then information seems to be lost, violating a fundamental rule of quantum mechanics. Imagine you have a book with all the details of a particular object. You send the book into a black hole, and the book disappears beyond the event horizon. Normally, you'd expect that the information about the book would still exist, just in a form we can't observe. However, Hawking's theory suggests that the book's information could simply vanish when the black hole evaporates. In this scenario, it's as if the book was never written in the first place, completely erased. This problem struck at the very foundation of quantum theory, which relies on the principle that information is never truly lost. If black holes could erase information, it would imply that quantum mechanics is incomplete or even wrong in its most fundamental principle. This gave rise to what's known as the information paradox, the question of whether information that falls into a black hole is lost forever, or whether there's a deeper, more complex way in which it's preserved. The information paradox has sparked decades of debate among the world's leading physicists. Some have argued that the information is indeed lost, suggesting that our understanding of quantum mechanics and black holes might need to be revised. But many others, including Leonard Susskind and Juan Maldacena, have fiercely defended the principle of information conservation. They have proposed various solutions to the paradox, which suggests that information may be encoded in ways we don't fully understand. One of the most prominent proposals comes from the idea of holography. This theory suggests that the information about what falls into a black hole might not be lost, but instead could be stored on the event horizon itself in a two-dimensional form. According to the holographic principle, the information about a three-dimensional object can be encoded on a two-dimensional surface, just as a hologram captures the 3D image on a flat surface. In this view, the black hole's event horizon may contain all the information about what has fallen into the black hole, and that information may be retrievable through the radiation emitted by the black hole, although not in a form we can directly detect. Another intriguing idea involves firewalls. The black hole firewall hypothesis proposed by physicists like Alessandro Strominger and Samir Mathur suggests that the event horizon might not be a smooth, featureless boundary as traditionally thought. Instead, it might be a region of intense energy like a firewall that could destroy anything that crosses it. If this is true, it could offer a way to preserve the information, albeit by fundamentally altering our understanding of the event horizon and what happens when matter falls into a black hole. However, this solution is highly controversial, and it would require a major revision of how we understand the nature of space and time. As of now, the information paradox remains unsolved. The discovery of Hawking radiation fundamentally altered our understanding of black holes, but it also introduced one of the deepest conundrums in modern physics. Theoretical physicists continue to wrestle with the paradox, and new ideas are constantly emerging. Some believe that the resolution might require a complete theory of quantum gravity, an understanding of how quantum mechanics and general relativity work together at the most fundamental level, which is still an open question. In the meantime, experiments are being designed to probe the nature of black holes and their event horizons, especially through the study of gravitational waves and the use of more advanced observational tools. These could one day provide crucial evidence about whether information can truly escape a black hole or if it is, in fact, lost forever. The information paradox challenges the very nature of reality itself, asking whether the universe adheres to the strict laws of quantum mechanics or whether black holes represent an exception, an object where the rules of physics as we know them break down. Whether the information is lost or preserved, this paradox is a window into some of the deepest mysteries of the cosmos, a mystery that might one day unlock new insights into the nature of space, time, and the fabric of reality itself. For now, the paradox remains, tantalizingly unresolved, a testament to the complexity and wonder of the universe we are still trying to understand. Advances in nuclear fusion research. Nuclear fusion is the process that powers the stars, including our Sun. It is the most efficient energy production method known to science, capable of producing massive amounts of energy by fusing light atomic nuclei, like hydrogen, into heavier elements, such as helium. For decades, scientists have been striving to replicate this process on Earth in the hopes of unlocking an almost limitless source of clean energy. But how far have we come in this quest? To understand the groundbreaking advances in nuclear fusion research, we need to trace the history of the field and explore the scientific breakthroughs that have shaped it. The story of nuclear fusion begins in the 1930s when physicists like Hans Bethe first unlocked the secrets of stellar fusion. Bethe's work revealed that stars, including our Sun, produce energy by fusing hydrogen atoms into helium through a series of nuclear reactions. This process, known as the proton-proton chain reaction, releases an enormous amount of energy in the form of light and heat, sustaining the star's brightness and temperature. Bethe's insights were groundbreaking and set the stage for future work in nuclear fusion on Earth. But it wasn't until the 1950s that humans seriously began trying to replicate fusion as an energy source. During this period, the concept of nuclear fusion reactors, machines capable of fusing atoms and harnessing their energy, began to take shape. The first steps in this direction came through the development of magnetic confinement fusion, a method that uses powerful magnetic fields to contain hot plasma, a superheated, electrically charged gas, in a controlled environment long enough to sustain fusion reactions. The concept of magnetic confinement led to the development of the tokamak, a donut-shaped reactor designed to keep plasma at extremely high temperatures, millions of degrees Celsius, without it touching the walls of the containment vessel. In the early 1960s, Soviet physicists, including Andrei Sakharov and Lev Artsimovich, made significant progress by designing the first tokamak reactors, which were capable of achieving the high temperatures needed for fusion. However, despite their promise, these early reactors were not able to maintain stable conditions or generate more energy than they consumed. Fusion, at least on Earth, was still elusive. The core challenge was that the plasma inside a fusion reactor had to be heated to temperatures far beyond the melting point of any known material, about 100 million degrees Celsius, while also being held together long enough to allow fusion reactions to take place. No materials existed that could withstand this extreme heat. Despite these obstacles, the dream of nuclear fusion never died. In fact, the past few decades have witnessed extraordinary progress, particularly with the advent of newer technologies and international collaboration. One of the most significant advances came with the development of the International Thermonuclear Experimental Reactor, ITER, a project aimed at building the world's largest and most advanced fusion reactor. ITER, located in southern France, is a collaborative effort involving 35 nations, including the European Union, the United States, China, and Russia. The goal of ITER is to demonstrate that fusion can be a practical and sustainable energy source by achieving a net positive energy output, meaning that the energy produced by the fusion reactions is greater than the energy put into heating and maintaining the plasma. ITER's design is based on the tokamak, but with cutting-edge technologies that allow it to operate at temperatures and pressures that were previously unattainable. In 2021, ITER achieved an important milestone by completing the installation of its superconducting magnets, which will play a key role in generating the magnetic fields necessary to contain the plasma. These magnets, which are chilled to near absolute zero, are able to generate stronger magnetic fields than conventional magnets, enabling ITER to achieve the temperatures and pressures needed for fusion. While ITER is still under construction and will not be fully operational until the late 2020s, fusion research has made significant strides through other experimental reactors. In 2021, a breakthrough came from a much smaller fusion facility, the National Ignition Facility, NIF, in the United States. The NIF's approach to fusion differs from the tokamak in that it uses laser-induced fusion, a process called inertial confinement fusion. Here, ultra-intense lasers are focused on a tiny pellet of hydrogen fuel, compressing it to extremely high temperatures and pressures, simulating the conditions found at the core of stars. In 2021, NIF announced that it had achieved a world record for fusion energy output, producing nearly 1.9 megajoules of energy from a fusion reaction, a major step toward the goal of achieving ignition, a state where the energy produced by the fusion reaction exceeds the energy required to initiate it. This milestone was significant because it demonstrated that fusion can occur under controlled laboratory conditions, and the results are pushing the boundaries of what is possible in fusion research. However, researchers still face significant challenges before fusion can become a reliable source of energy. The next step for NIF and similar facilities is to scale up the process and improve efficiency, ensuring that the fusion reactions are sustained over longer periods and generate more energy than they consume. Looking to the future, the advances in fusion research present a tantalizing possibility: clean, virtually limitless energy. Unlike nuclear fission, which powers current nuclear reactors but produces radioactive waste, fusion doesn't create long-lived radioactive byproducts. Its fuel, mainly isotopes of hydrogen, such as deuterium and tritium, is abundant, with deuterium found in seawater, making it a potentially inexhaustible resource. However, challenges remain. The sheer scale of the technology required to achieve sustained, net positive fusion reactions is immense. The reactors must be capable of handling the extreme conditions needed to keep plasma hot and stable, and new materials must be developed that can withstand these conditions without degrading. Additionally, the cost of building and maintaining these reactors is still very high. Despite these challenges, the rapid pace of innovation in fusion research is incredibly promising. As governments and private companies continue to invest in fusion technology, the dream of harnessing the power of the stars may one day become a reality, providing humanity with a revolutionary energy source for the future. The work of physicists, engineers, and researchers around the world is laying the groundwork for a cleaner, more sustainable planet powered by the same process that lights the night sky. For now, the race to achieve practical nuclear fusion continues, and every step forward in this field brings us closer to unlocking the greatest energy source known to science, one that could forever change the way we power our world.